It's now my pleasure to ask Roger Griffiths, General Manager, Assets and Engineering Service at Westpower, to moderate this morning's session. Roger has been around an awful long time within our industry and has made a very significant contribution, which we recognise by giving him life membership a couple of years ago. Roger spent the last 40 years working in the industry and is passionate about finding new ways of doing things. He strongly believes there's an exciting group of challenges coming with the new technology, and I think an exciting group of opportunities. And it's about an ever-changing customer experience, and we look forward to being a part of the wider industry response to those challenges. So Roger, thanks for taking time out to be the moderator today. I'll hand over to you. Thank you.
Thanks for that introduction, Peter, and welcome to everyone along to our second Asset Management Forum. It's all a little bit different, isn't it? So we're getting used to it, but nice to see so many there and so many names I've come across over my long time in the industry. So just a little bit of housekeeping. Please just turn off your cameras to save bandwidth and also your microphones. It'll make it a much more pleasant experience for everyone. At the end of the presentation, please ask questions. Don't be shy. The presenters love questions. So please ask questions. You can either do that by putting your electronic hand up, I'll see that. You can put your real hand up, but I probably won't see that. There's so many here. Or you can just propose a question in chat, and I'll keep an eye out for that, and I can propose a question to the presenter. So our first presenter is Alan Miller, who doesn't really need any introduction. He's a director and engineer of Alan Miller Consulting. Just a little bit of background on Alan. He's a consultant engineer. He provides independent expert advice in the electricity and technology industries. He's also a member of the EEA IPAG and a director of Network Tasman. His experience includes leadership and technical roles in the electricity and international high-tech industry. Probably many of us remember Alan from his time as a director at the Epicentre from 2011 to 2017 at the University of Canterbury. And he established and led the Green Grid Research Program that we're all benefiting from now. So over to you, Alan.
Thank you, Roger. Right, so I'm now going to share my screen, which has the presentation on it that I'm going to present today. Thank you for the opportunity to present this at the EEA's Asset Management Forum. Can everyone see that? Great. Okay. So this presentation is based on some work that was commissioned by the Ministry of Business, Innovation and Employment around about a year ago, but we started discussing it in August last year. Transpower was also involved in this. And the objectives of the study were to contribute to the Ministry of Business, Innovation and Employment's electricity demand and generation scenarios, or EDGEs as they are often called. And it's also to investigate the potential capacity and generation from utility scale solar, and that's megawatts versus time and location, also megawatt hours or gigawatt hours by time and location, and by network connection. It was also to contribute to Transpower and distributed planning, and to understand how solar might contribute to more renewable energy generation and ultimately New Zealand's net zero goal. And I should say too that small scale rooftop and commercial solar were excluded from the study. It was specifically focused on utility scale. And by utility scale, I mean anything from 1 megawatt to 200 megawatts considered in this study. We also focused on first generation crystalline silicon technology, which makes up about 90 to 95% of the solar market. So we didn't look at the new emerging technologies like perovskites and multi-junction cells and so on. What I'm going to cover in this presentation is, well, before I actually go on to that, I'll just say a few acknowledgements. It was commissioned by the Ministry of Business, Innovation and Employment. Transpower provided substantial support. PowerCo also provided data for the study, and numerous public sources were used for it, and those some listed there. And the last point on that slide is a link to the study. If that link's not working, you can just Google MB utility scale solar and it should bring up the report. So there's a large report which presents all of this work if anyone's interested in following up further with that. So I'm going to discuss today how we went about the study and the economics of solar, what the forecast uptake is and where it's forecast, and then just finish with a few key conclusions, and if we have time, maybe talk about some utility scale solar technology. So first of all, how we went about the study and the economics of solar. Well, the challenge with this was from the outset that when we started talking about this, there were no utility scale solar schemes in New Zealand. I think around the time we started talking about it, Marsden Point Oil Refinery announced that they were going to build a scheme. And between then and actually starting the study and undertaking it, Genesis Energy announced I think it was a 300 megawatt power purchase agreement for a solar scheme. And Kia Energy announced publicly that they were building one in Marlborough. And I think there may have been a few more talked about since then. The challenge, though, with an absence of no-built schemes is, what do you base your study on? So I proposed a method to consider a combination of land use, because solar is very much tied up with land, solar resource by location in New Zealand, because that varies substantially across New Zealand, grid capacity and proximity to transmission, and proximity to existing distribution lines, specifically 11 kV lines and zone substations. And also, it would consider the economics of solar in terms of net present value or achieving an acceptable rate of return. And then I sort of talk about a melting pot where we put all of those things into a single model and then let the best schemes with the highest NPV bubble up to the top. And there had been some work done internationally on considering resource and considering land use, and there'd also been some studies done on considering technical integration into the grid, but none of those studies brought all of that together in one place. And I think this is the first time this has been done in one single study. All of those have been brought together in a single study. So there's, in that red box there, is the single model that combines all of those things: land use, grid capacity, and cost of extending the grid to a solar farm, solar resource, solar costs, and electricity prices. And then that leads to solar farm rate of return. And I'll just go through the inputs to the model and talk about some of those. So first of all, land use and grid capacity. What we did was, using some information from Landcare Research, divide New Zealand into kilometre by kilometre cells. So there were nearly 270,000 of those to cover the whole of New Zealand. And from the Landcare Research database, it very usefully gave information on New Zealand down to that, which we were able to interpret into those kilometre by kilometre cells based on the type of land or the land use. And we included anything that was suitable for solar, we included as being grassland, either high producing, low producing, or depleted, and excluded much more than we included. So forests, native areas, national parks, crops, vineyards, orchards, and urban areas were all excluded, plus all of other things like open cast mines and so on. We built a model that considered the cost of that land, so the grassland, either high producing or depleted, and also considered its proximity to population centres. So that's what the first input. The second input is proximity to grid exit points and medium voltage lines. And the way the model works is, it actually builds a notional transmission line to the nearest grid exit point with suitable capacity to, and then builds that, incorporates that as a cost into the solar farm. That's for transmission connection. For distribution connected, it only considers land that is within a couple of kilometres, actually 1 kilometre, I think, of a medium voltage line. The assumption being that no small scale solar farm can really afford to build a large line connected to medium voltage. However, between 5 megawatts and 20 megawatts, we did consider them building a 33 kV line to the nearest zone substation, with the 11 kV line underbuilt, the existing 11 kV line. And this is what we got from that. So actually that first circle there on the top left, the land classes, taking the 270,000 cells and just considering the grassland, we actually ended up with 162,000 cells with some sort of grassland in them. But filtering that further to ensure there's enough grassland to actually build a solar farm and the surrounding cells have enough grassland, it filtered it down even further to 16% of those 270,000 cells. And in the case of distribution, you can see there on the map there, it's following these distribution lines. And in the report, I talk more about how we derived those medium voltage line paths. And so there's only 12% of the land suitable for distribution connected solar. So that's land use and grid capacity. The next thing to consider was solar resource. And this came from a large amount of work looking at every part of New Zealand by those kilometre by kilometre cells and looking at effectively over a year, how much energy a 1 kilowatt solar cell would produce or solar module would produce, and then that can be scaled. So you can see in areas like Marlborough, Nelson, Tasman, South Canterbury, the Mackenzie country and Otago, as well as the far north there and Bay of Plenty, Hawke's Bay, and even parts of the Waikato, the solar resource is very, very good compared to other parts of New Zealand like Southland, parts of Southland and parts of the West Coast and the Alps. So the capacity factor actually ranges quite significantly from 0.12 to 0.2 in New Zealand, and that is assuming fixed axis tracking, so east to west tracking systems, and also overcapacity of modules on a solar farm. That solar resource, the next thing to consider is solar costs, a really important input to a model looking out to 2060. And this is actually a two-step process. The first step was to forecast solar production worldwide, and then modify that by learning curves to work out what the eventual cost of solar would be. The idea being that a learning curve works on the basis that the cost of, in this case, solar modules or solar systems reduces by the learning curve for every doubling in production. But production can't continue to double forever. If we look at the last 10 years, it's doubled at a rate of about once every 3.6 years, solar production has doubled. But that surely can't go on forever. That would be a huge exponential. So what I did here is apply some reduction in doubling rates in this grey case, beginning to reduce from 2024, and this yellow case reducing from 2019. to give the classic sigma curve or S curve. And you can see matching that against forecasts from other organisations, the production levels do look like they match other forecasts quite well. So the next step was to modify that by learning curves, which I converted to annualized learning curves. And we get this in terms of declining costs. And I should point out that this axis here is dollars per watt peak on the AZ side, so it includes the inverter. It's in New Zealand dollars and it's in real terms. So it doesn't modify the cost by inflation over time. So it's actually comparable to 2020 costs. So for a 1 megawatt system in 2020, we're looking at $1.80 per watt. For a 200 megawatt system, economy of scale bring that down to $1.10 per watt. But out into 2060, that 200 megawatt system is costing 40 cents per watt in real terms. If we looked at this in nominal terms, these would actually increase as inflation starts to adjust, especially the labour cost component of installing these. And the report gives a lot more detail on this and how these were derived. But just to go to the next slide here, there's some breakdowns of the various components of cost of solar systems. The 1 megawatt one here, in the 200 megawatt, you can see that modules form a much larger part of a system's cost for a 200 megawatt. Next input, electricity prices by location, a very important input because it affects the revenue gained from, or determines the revenue gained from the solar, utility scale solar. This equation up here gives the revenue. The first part of that equation is quantity. So that's back to that slide 12, the map of New Zealand with the solar irradiance on it. So it does depend on location. Then there's average price by a reference node and by year, and then that's modified by a location factor for the GXP for a particular year. And then it's also modified by a solar weighting factor, which weights the price into periods when solar generates. So the price during nighttime, for example, is not relevant to solar production. And the other important thing was that this is a graph of location factor. So this LF term versus size of utility scale solar system. It was important to reflect the fact that as more generation occurs at a GXP, it effectively reduces demand, reduces losses, and therefore reduces the location factor. So that this graph just gives a few GXPs showing, for example, in the case of Blenheim, it's about 1.24 at 1 megawatt solar system, but as we come out to 200 megawatts, the location factor reduces to nearly 1.2. So the price for the energy reduces. And finally, economic assumptions. The Ministry of Business, Innovation and Employment provided these EDGES base case and scenario 1 and 2 assumptions. And essentially, they used a average price at Benmore, the reference node, based on previous EDGES scenarios. And essentially, they looked at changing electricity price inflation as well as the required rate of return of a solar farm, just to look at the sensitivities around that. And the output of all of this is, or was, a long list of potential systems by scenario, and anywhere between 0 and 40,000 systems. And a short list, and the short list was determined by anything that could connect within the existing capacity of the grid. And that was necessary to provide some upper level constraint on the optimization to determine the optimal solar size for each location. Otherwise, we'll get an open-ended optimization with the 40,000 systems and tens of gigawatts of solar forecast. Just on the subject of sensitivities, this is a graph of net present value versus variation from a reference value for all of these inputs to, you know, that melting pot of inputs I talked about, the box with the red line around it. And then down the right-hand side is it ranks those inputs in terms of their sensitivity. So at the very top here is our electricity price and capacity factor. So solar returns are most sensitive to our electricity price and capacity factor, or solar resource. The next is capital cost, and then cost of capital. So capital cost being this red line here, cost of capital, the discount rate being the purple line. And then sensitive to next is capacity, operation and maintenance cost, transmission cost, and land cost. And I'll return to transmission cost and land cost on the last slides, because while they're lowest on the list in terms of sensitivity, they actually are a lot more important in determining solar location than this list might give them credit for. So some results, what the forecast uptake is and where it's forecast to uptake. So we'll first start by looking at this first case, or scenario 2 under the Aegis scenario, which looks at a low rate of return requirement of 6.5% and high electricity price inflation of 3%, which runs above the historical average. And that gives these results. Note that the map on the left there is 2020 to 24. The one on the right is 25 to 29. So to my surprise, the first locations for solar were in the Mackenzie area in the Waitaki Valley. And then if 5 years later, a lot of Canterbury, Nelson, Tasman, Marlborough, and in the North Island, the Bay of Plenty, Hawke's Bay, Manawatu, Waikato, Auckland, and Northland, and I think that's actually the Marsden Point oil refinery there, and some in Taranaki as well. The interesting thing is, why did these locate here? Well, it's actually related to the cost of solar resource, solar resource, which is excellent there, but it's pretty much the same as, say, Nelson, Marlborough. It's also related to transmission cost. It's lower cost connecting to transmission, but importantly, land cost is lower than, say, Nelson or Marlborough or other places in the North Island. We look at this other scenario, higher rate of return requirement and lower average electricity price inflation. Then this map on the left is actually 2025, and we can see that this one in Nelson does locate then. And then in 2030, we're now looking at additional sites in Marlborough, Bay of Plenty, Hawke's Bay, and Waikato. I think that's near Raglan there. And that was transmission connected. If we look at distribution connected, with the low rate of return requirement and higher electricity price inflation, a lot in Nelson, Tasman, Marlborough, Canterbury, some in Bay of Plenty, and a lot in the far north as well, Northland in the far north. And then 5 years later, just really all over the place. And what this indicates is, the uptake could be very rapid in the space of 5 to 10 years. Back to a higher rate of return requirement and lower average electricity price inflation. The first ones to locate in 2030 are around Nelson, Marlborough, and the far north. And then, more in Nelson, Marlborough, far north, Canterbury, Bay of Plenty, Hawke's Bay, Waikato, and Northland in the far north. There's far more results in the report if anyone's interested in looking at them in more detail. In terms of capacity uptake, depending on the scenario, we're looking at some in 2020, a lot in 2025, and a very rapid uptake there. At 2,000 megawatts of capacity, it would require about 5,700 hectares To put that into context, I think it's about 30,000 hectares used in vineyards in New Zealand at the moment. That would generate around 3,500 gigawatt hours. And back of the envelope calculation I did last night shows I think that would be somewhere between 3 and 4 megatons of greenhouse gas reduction, depending, of course, on what thermal generation would have been alternatively. And I think just in terms of key conclusions, there's a significant amount of land available for solar, enough for many tens of gigawatts. However, land and transmission proximity will be greater determinants than the NPV sensitivity indicates. In my experience, people start from, a lot of companies start from the point of view of, we have some land here, what can we do with it? Solar is a possibility, let's look at putting solar on it. Or most other inputs are roughly equal, so it's therefore land and transmission or distribution connection cost that just determines the most favourable areas. Transmission connected systems appear to be more economic in the first instance than distribution connected systems, although I note that it's mainly distribution systems that are going ahead at the moment. Capacity of distribution connected solar is around 5 to 15% that of transmission connected solar. And when looking at these forecasts, you need to look at them in conjunction with changes that may affect electricity price and location factors. High uptake may also depress wholesale prices, negating the high rate of return in forecasts. So these forecasts didn't look at those structural changes to the market that may occur from more generation, apart from location factor adjustment. Forecasts are also sensitive to worldwide solar production, as I showed in that cost of solar graph. Lower cost of capital may give rise to more projects, and we need to balance that with potentially lower electricity price inflation. And the lower cost of capital, as we're seeing Reserve Bank or central banks are bringing down interest rates substantially, lowering the cost of capital to projects. Once economic and under development, solar capacity could increase very rapidly over a period of 10 to 15 years. And I'll hand back to Roger now for questions.
Well, thank you very much for that, Alan. That was an excellent presentation. Really opened up my mind to the potential out there for solar. So I didn't want to disturb you. It's such a great presentation. We've only got a few moments left of the initial time. So would anyone like to raise any questions? Now, we did tell you not to be shy, so please feel free to put your hand up. Otherwise, I would be happy to ask one or two. Really early on, Alan, you said you just focused on the current crystalline technology, but then you mentioned some new tech. How much of an impact do you think that will have on A, the cost, or B, the production, and will that have an impact on your analysis?
Yeah, I see the new technologies as something that effectively contribute to that learning curve effect, where there's constantly R&D going into solar technology, improving it's both a capacity factor of solar schemes as well as bringing new products onto the market and then go into production and onto the market, which just creates more options, more competition, and brings prices down. So, whilst we're focused on crystalline silicon, which is the dominant technology at the moment, those other technologies will come into play and continue that learning curve effect. Yeah.
Okay, no, thank you for explaining that. I do have another question for you around, I guess, the impact on the network. If a whole lot of the solar did really take off, we had a huge penetration happening out there. Clearly, it's highly variable at times. Do you think that will have an impact on the, let's say, the priority stack of what's chosen next? And will that maybe mean that solar is either less or more valuable than some other forms of generation that might be being looked at?
Yeah, well, the nature of solar is it'll generate when it generates. And unless there's some sort of technical constraint, it will be allowed on the network. So it'll have an net effect of reducing demand. Very large schemes might offer into the market. I do actually think solar works well with our hydro, in that the hydro forms, or it can be a short-term form of storage effectively, just by backing off hydro generation while solar is generating. I think there could be opportunities. There will be technical issues likely to occur especially on 11 kV networks, rapid variation of solar and that kind of thing. So that's important to look at and assess, as well as affecting voltage quality. In terms of connecting to the grid, probably not so many issues. I mean, it's still very, very important to consider those technical issues before it's connected. Yeah, I do think solar works well with hydro. I think there's also opportunity for overcapacity of solar in terms of, rather than spilling it, storing it as energy in hydro.
Well, thank you, Alan. We have a question that's coming on the chat. As an extra return on investment, have you considered the multi-purpose use of land during generation, e.g. wind farms still allowing farming during generation? Would that work for solar?
Yeah, I mean, people have talked about it, growing crops and things under solar. It's not something I know a lot about. I would have thought, that by its nature, the solar is reducing the sun available to grow crops or grow crops for grazing. But if you can make it work, then obviously you can make more money from that land. So it improves the economics.
Thank you very, very much, Alan. A wonderful presentation. Thank you for taking the time to present that exciting work to us.
Yeah, thanks for the opportunity.
Well, next on the program this morning, we have Murray Henderson, who's the Principal Market Advisor for Transpower. And Murray's going to be talking to us about distributed energy resources. Now, Murray has over 14 years of experience at Transpower working to deliver the system operator service. And he's worked on most of the changes, the major changes anyway, to the wholesale electricity market. A key focus recently has been the Electricity Authority's Real-Time Pricing Initiative, or RTP. It's another acronym we're going to have to get used to. So RTP is going to be the biggest change to the electricity market and, in fact, Transpower's market system since their relative inceptions. And so part of Murray's current role is to consider how Transpower's delivery of the system operator service might be required to change in the future, including as a response to DER, another three-letter acronym there, or distributed energy resources. So Murray's the system operator observer for the Electricity Authority's Market Development Advisory Group. So over to you, Murray.
Morning. I can't seem to get my video going because it's telling me the host has stopped it, but that's not a problem. Even though I did iron my shirt this morning, we'll just crack into the, oh, no, here we go. Now I'm being allowed to, here we go. Good morning, everybody. So as Roger said, I've been at Transpower working primarily on delivery of the system operator service for a wee while now. I'm not an engineer in any way, shape or form by trade, so this has the potential for me to get into some very uncomfortable areas. But thankfully, this presentation is really talking about money as opposed to technical engineering aspects. So hopefully it's of interest to you, and it does sort of follow on a little bit from Alan's excellent presentation earlier. So I will now start sharing my screen. So can we all see that?
Yes, thanks.
It's good,
You
Murray.
can? It's good? Okay, cool. So the question there is, does DER stack up in New Zealand? And I generally try and throw in a few jokes and a bit of interest into my presentations, but it's going to be interesting to see how that goes, given that I'm basically in a phone booth talking to myself at Transpare headquarters. So here we go. So does DER stack up in New Zealand? Yes. So that was going to be a joke about, you know, you can go off to morning tea early, but of course it's not catered, so that doesn't really work. So we'll crack on to the next slide of how do we think we know that? So with our role as system operator, as Roger said, there's a lot of change that we expect to be coming. And we commissioned some authors via Sapere, and I know it'll be a little bit funny the way we talk about this, but Sapere runs an independent expert contracting. So it's not a Sapere report. Sapere is the company they work for. The report is the report of the authors themselves, and those three people were David Reeve, Karina Commandant, and Toby Stevenson. So there's a couple of very well-known names there for a lot of you, I imagine. And we asked them to explore the potential value of DER to the power system, what uses DER could be encouraged to supply with the right pricing. And there was a lot of debate around that word pricing because the authors themselves preferred incentives, which they preferred because it would include the use of things like standards. And I'm sure most of you will be aware there's been a lot of discussion in the industry around inverter standards and how can we get the right one and all of the correct legislations that it needs to be in, so that all the equipment that's going in will actually help and not cause any avoidable issues to the quality of the New Zealand power system. And we also asked them, the report authors, to look at what are the current barriers and transaction costs. And the link that when we send the slides out is there, will take you to a page on the Transpower website, and you've got a menu, if you like, of options of how to consume the report. There's a 15-page Transpower very executive summary of the report. There's a 30-page summary of the report by the authors in PowerPoint format, and then there's the report itself, which is about 100-odd pages long. So why did we ask? So DER is here and now and growing, and you know, Alan's excellent presentation showed the potential for solar, and of course solar is only one part of the potential distributed energy. At the moment, it's going in on the basis of self-benefit. So people are using their environmental concerns, you know, whether they're purchasing a petrol vehicle or a battery vehicle, whether they're putting solar on their roofs. It's all currently the way that the rewards work for distributed energy. It's primarily delivering personal benefits. But when we look forward to future scenarios like Transpower has put out under Whakamana i Te Māori Hiko, and there's a link there in the slide to all of Transpower's forward-looking strategy documents. We believe that DER will play a role in a transition to a smart grid which uses renewable electricity to meet all our energy needs. And what we're really driving at there is in Whakamana i Te Māori Hiko, there's a near doubling of electricity consumption, but the peaks don't go up by 2. Because we believe the most efficient use of all the resources available would be to use distributed energy resources and other mechanisms to shift load off the peak. Because all of you that are involved in networks and generation and anyone that's involved in transmission all know that it's the peaks that really drive the bulk of the costs. And those costs are paid collectively by ourselves as a country. And if we can take steps where we're using resources that are already connected, or we can incentivize the connection of newer assets and different assets to what we have traditionally used, if we can harness those to move energy off the peak, we can lower those costs. Another aspect of that is, you know, from an egocentric point of view, if you like, as the deliverer of the system operator service, we provide all the ancillary services to the market at the moment. So things like instantaneous reserve, frequency keeping, black start, all of those other ancillary services, that all sits with Transpower as the system operator to decide what's needed, deliver those services, and to actually go out and procure those. And we also have, as Roger mentioned, we've got a vested interest because our software is the basis for the market, and we also are operating and dispatching the power system. So we've got a heightened interest in what might be coming at us down the line, because ultimately we'll have to deal with it. So what did the authors find? So their definition of DER that they used, they pretty much included everything bar the kitchen sink, which we think was the best way to do. So distributed generation itself, battery storage systems, DR, which has included hot water ripple control, electric vehicles, which of course batteries on wheels, and that last one will become apparent when we talk about the services and the value streams. And when the authors were conducting the study, so they leveraged off Whakamana i Te Māori Hiko. They also looked at the Productivity Commission's Low Emissions Economy report, the Interim Climate Change Committee's Accelerated Electrification report as well. So it's not, you know, it was truly independent. It wasn't rebadging any of Transpower's strategic work. And sorry, I just had a little beep from Zoom there. And when they undertook the report, they sort of worked in three stages. So they estimated the potential value, so which was largely based off current market conditions. Then they evaluated the potential supply. So they considered the pricing and the need for each service to create supply and demand functions. And then lastly, they identified the barriers to greater access and deployment of distributed energy resources. The value streams that they considered are all listed there. So energy arbitrage, so that's buying energy when it's cheap, storing it, and then injecting it back into the power system when the prices have gone higher. So clearly you need some form of storage, so that's really targeting at batteries. Resource adequacy is, you'll see later, is the biggest one. So what they've included in resource adequacy is distribution avoidance, so avoiding cost for increasing the size of the distribution networks. Similarly, avoiding the costs of increasing the size of the transmission network. And lastly, they have included in that umbrella flag, avoiding the need for increased generation capacity to meet the needs going forward. Instantaneous reserve, so that's the ancillary service product that we as the system operator procure to restore frequency to the normal bands following a disturbance. There's been a lot of discussion around that historically, around what the right products are going forward. So that will always be a sort of a moving feast. And of course, things like batteries are incredibly fast at responding. So, you know, it may be that you need less in the future if you're harnessing distributed energy resources, because they do a better job than waiting for a unit that's tail water depressed, for example. Frequency keeping, so that's the constant frequency regulation. At the moment, we procure a 15 megawatt up and down band across, or from the generation fleet, to keep the small imbalances between demand and supply balanced. Voltage services, so that would be that you are providing a voltage support either to your distributor or into the transmission network to keep voltages within their allowable limits. Simulated inertia is work that we're undertaking now in Transpower, looking and thinking in our forecast future with less large spinny things connected to the network. How will the network respond when we have frequency disturbances, because we don't have all those big heavy spinny things that are going to keep the frequency stable, or as stable as it is now. Black start is something we've thankfully tested and never had to really use. where part of the network is dead, and then you're providing a service, an ability to restart and reliven that part of the network. That might be something which maybe with the size of the units that would be distributed might be something which is more valuable to distributors rather than to the transmission level. But no one, you know, we're always looking into the future, but no one's entirely sure what it's going to look like. Harmonics links back to that comment about ancillary sort of products for DER, because the authors noted that when we get a lot of DER connected into the distribution networks, there's the potential that they may disturb and actually harm the power quality. And so there may be a need in the future for harmonic support within the distribution networks to restore the power quality back to what it was. If any of you have read the Rocky Mountain Institute study on batteries and what batteries can do, they've got 13 services. The difference between the 7, well, actually there's 8 there, the 8 that are listed there and the 13 is that resource adequacy has grouped up quite a few of those that the Rocky Mountain Institute listed. And the other thing is that it hasn't included any of the personal benefits, such as lower bills or lower distribution costs because you're avoiding time of use, etc. So that's the difference, if anyone was wondering why the Rocky Mountain Institute has a different number. A concept which is quite important for understanding the value of distributed assets and or earning potential is that they're able to provide many services. So you can see there on the graph that providing, you've got a black bar, which is your costs. You get paid for providing benefit 1, the blue amount, the green amount for benefit 2, and the yellow amount for benefit 3. Individually, none of those return value to the owner of the distributed resource. But if you set up markets and structures such that people can participate in multiple markets and you're able to stack them all up, then they do make sense. And that's that concept of value stacking. It's important to note when we're talking about value stacking that there's an absolute bottom line that physical double dipping is not okay. So if a distributed energy resource was offering into the instantaneous reserve market and being cleared in the instantaneous reserve market, but they were also participating in a distribution increase avoidance trial, so a demand response program, and they were turned off as part of the demand response program, or in the case of a battery, they were turned on and they were running at maximum and they were physically unable to deliver the instantaneous reserve, then that's obviously problematic, because at some point people are relying on that physical delivery to maintain the power system or the distribution network, and you're being paid for something, so you have to deliver it. On the other side, it's possible that financial double dipping may be okay, and that's really up to the people that are paying those services. So the best example there is if a part of the transmission network is running hot with the loads, and the part of the distribution network that's being fed from that part of the transmission grid is also running hot. If the distributor calls for a demand response program and Transpower as the grid owner calls for a demand response program, if the load goes away, if you turn off or if you turn your battery on, then you've met the needs of both parties. So there's an argument that can be made there that you should be paid twice. And I guess the thing there is that in the worst case, you don't want people ending up into a blinking contest and both systems run hot because neither party wants to make a call because they're both waiting for the other party to make the call first. So there's a big challenge around the coordination of physical delivery, but it is being done overseas, and there's absolutely no doubt that it can be done here. Looking at the value stack assessment results, these are all, looking at the size of the pie. So how much could be derived from the current market pricing, etc. And they've got values at 2020, 2035, 2050. As you can see, by far the biggest potential value stream comes from resource adequacy, and the report authors found that it's reasonably evenly balanced, I suppose, between the three costs in there of transmission, distribution, and generation. And in fact, each of transmission, distribution, and generation avoidance is bigger potential earners by far than any of the other services that can be provided. So energy arbitrage comes in third, and simulated inertia is second. And you'll notice that harmonics actually ends up being a cost. And frequency keeping is an interesting one, in that there's the potential that if we end up with vast uptake of batteries in particular, that the way that batteries can be set to respond means that potentially they're all doing mini frequency keeping, and collectively across the whole network, it means that your actual need for a frequency keeper per se evaporates, and so the cost goes down to zero. The cost and the potential value goes down to zero. The last column there is whether the services are additive. So this is in terms of your potential to value stack, and the only one that isn't is voltage. So the others you could, if the markets and the structures and the frameworks and the operating obligations were all set up in complementary ways, you could conceivably have a distributed energy resource that participates in all of those services concurrently and offers into the market or markets. And looking in a little bit of detail about assessing the service value streams. So they're all maximums, because what DER would be doing would effectively be displacing something else which was more expensive. So when, particularly for the resource adequacy aspect of the value stream. So when the report authors were looking through, they came up with costs per megawatt per annum for an increase in generation, for an increase in transmission, and for an increase in distribution. And those are the three values at the bottom there. The generation one is slightly different to the other two in that it's a net position. So you save money by using distributed energy resources by not putting in a peaking plant, but you also need to increase your baseload generation. So that figure there is the saving for not having a gas-fired peaker, the increased cost of having a baseload geothermal plant, and they've also included carbon tax in those numbers. I guess for the audience we've got here, there's a question around reliability and where does the risk sit, in terms of if you there's a comfort for those of us in the organisation who are transmission companies or distribution companies around building poles and wires, because it's a very well-known, understood technology. It's very much what you see is what you get. But when we're considering a brave new future with a lot of distributed energy resources, it's worth remembering that our poles and wires aren't infallible. So we shouldn't be trying to hold distributed energy resources to higher standards than our own asset reliabilities can deliver at the moment. Some more additional key findings. The hope or the expectation is that electricity will become simpler for consumers, but the flip side of that is that it's more complex for everybody else involved in the supply chain. For quantities, they were envisaging between 2.5 and 3 gigawatts of DER could be installed by 2035 if the incentives are right, and then an additional 1.5 gigawatts by 2050. So our current winter evening peak grid delivered electricity is sitting around sort of the 6.5 to 7,000 gigawatts. So heading out to 2050, you know, there's the potential there for 3.5 to 4.5 gigawatts. So, you know, sort of 2/3, 3/4 of our current winter peak loads could potentially be supplied by distributed energy resources going out to 2050. DER is going to be multiple technologies. So when we're considering and working out as an industry how to integrate those, we really want to try and get on the front foot and make these technology agnostic. We're striking problems at the moment trying to integrate batteries into reserve markets and frequency keeping and things, and our tools and our current legislative framework are all technology specific. So we're striking problems there, and we'd really want to avoid making the same issues again in the future. And it's a little bit chicken and eggy in terms of, do you integrate DER without knowing exactly what the uptake's going to be, or do you wait and see? And the risk and reward for going early or making it our decisions as followers is, if we go early, we're basing everything off assumptions, and the risk there is that we overcapitalize if the DER uptake isn't as assumed. You know, we spent a bit of money as an industry in the wholesale market putting in dispatchable demand, and we currently have one participant. You know, the expectation was there would be multiple participants. Similarly, we put in demand side bidding and forecasting, which enabled people to bid variations of their consumption into the market, and nobody uses that facility. But I think DER is going to be much more ubiquitous than that, and that there are all the Googles and the Amazons and the local entrepreneurs and software developers who are, you know, that they've got the platforms, they've got the ideas, and to that point earlier, that if you make electricity easier for the consumer, you will get that participation by default, because they're not really actively participating. A black box is doing it for them. If we make things just in time, then we risk lower uptake, and that people won't put in the capabilities into the assets that we ideally would want. So there's a philosophical kind of question there, and the report authors themselves also posed some very important questions. With the leadership, David Reeve pointed out to me that one of the problems we have is that, or one of the challenges rather, is generation is regulated as a competitive industry, transmission is regulated as a monopoly, distribution is regulated as a monopoly, and then the retail market is regulated as competition. So you've got two different types of regulation, two different regulators, and distributed energy resources goes across the full span of that. So, you know, where's the leadership going to come from? Are people ready for a difficult transition? You know, we're saying and we're thinking that DER is going to really take off. There's a few settings, you know, it only takes the government to put an incentive or a subsidy on something, and we're on the back foot, because we're like Australia, and solar PV's gone through the roof, and none of the, you know, the market and the established industry is trying to play catch up. And that last point is quite a key one, that DER is going to span so many traditional non-market participants. How do we engage with them all? We're already battling that with real-time pricing, trying to get out and contact people who, you know, may want to participate in the market or may benefit from it, but don't know about the industry. So that's that. Thank you.
Thank you very much for that, Murray. I didn't want to interrupt you again. I was just about to tell you we've got 5 minutes to run, but you pulled it together very nicely. That was a really interesting presentation, looking forward at what might be happening in the future. And I noticed at the end you posed a series of questions. This is all based on assumptions. Do we go early? Do we wait to see what happens? There were the questions, but I was really interested in your view. Do you think we should go early with this and really drive it, or do you think we should wait a bit longer and see what happens?
Yeah, I'd say we should be going early. At the very least, we should be, and this has been talked about by a few people, we should at least work out what our plans are. So maybe you don't push button on go, but we at least do, you break the back of the work that you need to do so that we've got a plan for how we would integrate it, rather than as we are now, where there's been a megawatt battery sitting at Southdown for potentially a couple of years, and at the moment they can only participate in the reserve market when they're charging by interrupting the charging, so they get considered to be interruptible load because they can't provide injectable load at the moment as reserve, because the definitions within the rules of the market say that the three types of reserve are interruptible load, tailwater depressed, or partly loaded spinning reserve. So that it doesn't fit within those boxes. And when we think about things going forward, at the very least, I'd say that we need to have the plans in place, if not necessarily having pushed go on making all those changes.
Cool. Thank you for that, Murray. We have another, perhaps a slightly provocative question here for you. In New Zealand, will Transpower System Operator continue to be the central role as the facilitator of the market, or do you see EDBs as a potential DSO for DER?
Good question. I don't think, there will always need to be a transmission system operator. So, there'll always need to be coordination between the distribution networks and nationally. It would seem highly unlikely that the sunk costs of the existing national grid and the generation fleet are going anywhere overnight. So there'll always be supply into the distribution networks that will need to be coordinated. And then I suppose the question then is, what's the products and services and assets that are going to be coordinated? So it would seem unlikely that a distribution network would have so much generation connected within their network that they would be a net exporter of energy. It's not implausible, but it seems unlikely. So there's always going to be sort of supply going into distribution networks. And then the question is, that they can, of course, they can ultimately very happily coexist once people work out what the needs are. So a point that's been made to me a lot is that within the distribution networks, it's apparently voltage which is often the issue rather than capacity. So it may be that the network company is working as a DSO, if you like, to control assets within their own network for voltage management issues within their own network. And it wouldn't seem likely that would be something that would be the role of a central system operator, because we clearly don't have any visibility down within the distribution networks. And if that was the case, then we'd need to, the big question is around coordination and sharing of information, because what DSOs could clearly exist. The TSO is always going to be there. And then it's the coordination between the two, so that it's that sort of physical double dipping issue where you want to make sure that neither party is relying on resources that the other one is controlling in a way that the other party doesn't want to. But at this stage, we think it should all be very complementary if DSOs were to exist.
Thank you for that, Murray. There you go, a new model, a hybrid model, DSOs and TSOs working collaboratively. That's what we can aim for. Thank you very, very much, Murray, for that excellent thought-provoking presentation this morning.
You're welcome. Have a good day.
Thank you. Well, we're going to move along now to the next presenter. This is Ryan Tulabing, who is a PhD candidate from Auckland University. The title of his presentation is Merits of Localized Demand Control in Preparing Local Distribution Grids for High Penetration of Solar PV and Electric Vehicles. Just give you a bit of background on Ryan. He got his electrical engineering degree from the Philippines, and he's worked as a maintenance engineer at a 300 MVA coal-fired power plant, and then as a project engineer for Nestle in the Philippines. He then took a joint master's in management and engineering of environment and energy at École des Mines du Nord in France and Universidad Politécnica de Madrid in Spain. Hopefully my pronunciation isn't too bad there, but you've certainly been around, Ryan. Currently, he is finishing his PhD degree about localized demand control at the University of Auckland. So over to you, Ryan.
Thank you very much. Yeah, the pronunciation is quite right. So I'm going to share my screen now. Yeah, so my topic for my PhD dissertation is about the localized demand control and how it can help in managing increasing penetration of solar PV and electric vehicles, particularly to the local grids. So this research is funded by the New Zealand Ministry of Business, Innovation and Employment. And my teammates are Brian Mitchell, Jason James, Hee-Chung Park, John Boyce, Soran Salchik, and Grant Kovic. So this afternoon, I will discuss first the background of this research study, and then the proposed solutions. And then I will talk or explain more about the localized demand control. Then we'll look into a case study and look at the results and discuss the results, and finally make a conclusion. So this research is motivated by the fact that, as been discussed by previous presenters, there's been increasing adoption of distributed energy resources, particularly solar PV and electric vehicles. And this is quite true, particularly in the residential networks as well. So the main motivation for this trend is that there is a decreasing prices for both technologies, as well as there is an increasing pressure for to achieve the sustainability goals of the different stakeholders or different countries all over the world. So as you see in the screen, I took this data from the EMI and the Transport Agency for New Zealand. This is the adoption rate of solar PV and electric vehicles. The electric vehicle is based on the registration percentage with the electric vehicles compared to the total vehicles being registered, while the PV adoption is based on the percentage of registered solar PV on the ICPs. The issue with this increasing adoption of distributed energy resources is that they are known to be intermittent, because sun changes all the time. I mean, the clouds cover the sun most often, and they are quite difficult to predict. And another thing is that the combination of these two technologies increase the demands, primarily due to the electric vehicle, and in particular in the residential networks, because the parking schedule of these electric vehicles somehow coincide with the existing peak demand already in the residential networks. So these peak demands causes overloading under voltage. Meanwhile, during the day in the residential networks where there's already a minimum demand for electricity, this is further reduced by increasing adoption of the solar PV on the rooftop on the residential networks. So the trend will this will cause reverse power flow and overvoltage. With this trend, the load factor in the residential networks will greatly suffer, as you've seen here in the graph. The problem with reduced load factor is that we paid a big amount up to this level for the capacity, while the main revenue is only based on the average. So if we increase the adoption of these distributed energy resources in residential networks, we would increase the peaks and reduce the minimum demand, but somehow the average are quite the same. So the traditional solution for this is to increase the system capacity, because we need to cater whatever the peak demand is. But this investment is quite risky, because as you've seen, the revenue is quite stagnant, and the system efficiency suffers. And this may lead to higher cost of power delivery, or longer return of investment if the regulatory body would limit the increase in costs. So there is not a solution being adopted, which is called the non-wire solution, and particularly called the demand side management. However, the demand side management is somewhat usually implemented in a wider scope, and they are blind to the local issues of the grid. And types of local demand side management is presented here. So in increasing speed of response and granularity of control, you have in terms of years, months, and day ahead and day off, and within 15 minutes. And you have two types of demand response here. You have the price-based demand response and the incentive-based demand response. So we already know about time of use, day ahead, or somebody already mentioned about the real-time pricing, and also the critical peak pricing, which is somehow a hybrid between time of use and RTP. In the incentive-based demand response, what we are actually more interested in is the direct load control in our research, because it's quite capable in addressing local grid issues, and it is also fast and could hold potential benefits for the local grid as well as the wider grid. So we established the design criteria for the solution of this issue. First is that the solution should be able to control the aggregated demand at the transformer level. This would somehow permanently reduce the peaks, and it should respond to utility requests or the operator. It should also be localized, so it can see what's happening in the local grid, but also can be scaled up to a bigger grid. It should be autonomous, and it should consider the user comfort, and it should be fair to all of the participants. That means the burden of responding to a particular grid event should be shared by everyone fairly. And the user privacy should be respected. So we decided so that there should be no central server that collects the user data. So I'm going to introduce the localized demand control. It's actually based on the local grid up to the local transformer. So this is a typical arrangement of a local grid. You have a transformer distributed power to different houses in different phases. And some houses would have some local generation, and they have the different types of appliances. In order to convert a typical local grid, you just need two types of devices. You need the LDC injector or signal injector at the transformer point, and then you have the control dongles at the devices. So what we did is we classified the different loads according to thermostat control, battery-based, and non-urgent and urgent loads. urgent loads cannot be controlled. These are the loads that needs to be adequate quick response or has direct interaction with the user. Meanwhile, non-urgent loads, for example, dishwashers and laundry, which can be delayed. Battery-based are electric vehicles and storage, while thermostat controls are loads that are controlled by thermostat to maintain a particular temperature of the thermal zone. So this system works according to this algorithm. It's a feedback loop control wherein the LDC signal injector would monitor the aggregated demand at the transformer area. And if the demand is increased, the demand is higher than its set point, which is set by the utility operator or upon the installation of the device, then it would decrease the signal frequency. That would mean to reduce the amount of load or the aggregated demand. And the dongle would respond to this signal by comparing the signal command to its priority level. So if its priority is higher, then it will stay on. If its priority is lower, then it will turn off. So if we look at this graph here, if we increase the signal frequency, we have different types of devices here. As we increase the signal, command signal, different types of devices would turn on. And we have the special case for battery. So you have grid to battery. That means the battery would charge, but if the signal is lower than it's set with its priority, it will discharge. Meanwhile, for the local generation, there's a certain threshold wherein it will start to reduce its output. This is to avoid the reverse power flow. So why we can do this? Because some loads are flexible. So we define flexibility of the load based on their operating conditions. So for cooling, we have this setup. So the main formula for flexibility is just the flexibility space divided by the total operation horizon. So this for heating is the reverse. While for the electric vehicle charging, we consider the time of use of the electric vehicle and the target state of charge. So the algorithm should be able to predict how long the battery will reach the target charge and then use that remaining time as the flexibility space so it can delay its charging. For the non-urgent loads, it's quite similar to the electric vehicle, but it uses the time as well for the latest finish of its job. For the battery storage, the flexibility is based on the state of charge. So the system model is based on physics and statistics and demand profiles. And you have, once you already have the power demand model, you need the schedule model, which is provided by, we took from brands and from usage profiles from different database collected on actual usage or actual user demand in different parts of the world. And then you have the load distribution based on energy baseline study and demand trends, and then benchmark for local grid setup. So this is how we run the simulation. I may have to skip this, but you can look at it if you download this. In order to test the algorithm of the system, we set up an actual microgrid at Ardmore. So these are the details of the system. These are the actual two houses. This house is we furnished with actual appliances and furnitures to act as a real house, while the second house is divided into four to emulate four houses. We have real loads such as water heaters and heat pumps to actually see the actual reaction of the algorithm. And these are the other devices on the microgrid setup. We have the signal injector and the load emulator for all other types of loads. And you have the control dongles. and you have the controller for the solar panels and the battery. We also developed a user interface for the microgrid status. So we see here the demand of the microgrid, and it changes based on the set points. And you can see the per phase demand and the voltages. There are other data that are not shown here because I have to cut the picture. So what you can do with this GUI is that you can set the target demand either manually or automatically by averaging per every 1 hour. We also created a home server for the end users for them to see their total demand and the disaggregated demand on different appliances. You can also see the priorities of their appliances, and they can change this. So for case study, we conducted a simulation study for a 60-house local network based on a benchmark residential network, which is consistent on the New Zealand networks according to Watson and his colleagues. So the local system is 300 kVA, composed 60 houses, and then it averaged 40 meters apart per ICP. It is done within 2 seasons, winter and summer, so that we will capture the highest output of solar PV and highest demand during the winter. So there are 2 cases here. First is we compare the LDC case versus no LDC. And then the second case is, second study is we kept the DER adoption of 40% and vary the adoption of the LDC system. So these are the distribution of loads in the local grid that we are simulating. So this is the result. The first graph, the graph on top is the case without the LDC. This particular graph is 40% DER adoption. So you see you have the solar output here at the bottom, and you can see an actual reverse power flow because of too much production of local generation, local grid. And you have high peak load because of the electric vehicles. This part is the electric vehicles. Meanwhile, if we look at the LDC case, the peaks are reduced while the generations are curtailed to avoid the reverse power flow. So this simulation, the set point is just set as the running average on the past 1 hour. So it has enough flexibility to adjust on the demand of the users while trying to maintain a flat demand. So we've run all of the cases, and then if we increase the DER adoption, you can see somehow a familiar duck curve. This 2 graphs, top and bottom on the left, without LDC, and the right have the LDC. The top graphs are for summer, the bottom graphs are for winter. If we increase the DER adoption, there would come a time when we exceed the capacity of the grid or local grid. However, if we introduce local demand control, the grid capacity will stay intact, will be respected. So the load factor is computed for each DER adoption, and we can see the trend of reducing load factor as we increase the DER adoption. However, it's consistent that we use the LDC system, we increase the load factor. Meanwhile, in here, while keeping the DER at 40%, we increase the adoption of the LDC system, and also the load factor is also increased. So in summary, the LDC merits and potentials are this. So we start at the functionalities of the LDC. It simply is a way to shift local demand, and then it can curtail local generation, and it automatically manages storage and battery-based loads. So with all this, it can follow the target net demand at the transformer level. And with these functionalities, you can have reduced peaks, you can increase the load factor, you can avoid reverse power, and you can integrate more solar panels and electric vehicles. And the implication of this is to defer costly upgrades and increase the utilization of existing assets. And for future applications, it can be used for dispatchable demand. If we allow the utility operator to send command to the transformers. And they can now also have a better load forecasting because they decide the set point of the demand. And it can also be used as ancillary services by basing the set point on the frequency or the voltage. It can also assist Blackstart by lowering its demand so that the running of the Blackstart generation would not be overloaded. It can also has the potential to bid for demand response services in the future, and it can manage the vehicle to grid because its vehicles are just batteries on wheels. Implication is that you have another opportunity for revenue stream and the savings due to deferred capex, which can reduce the power cost or power cost of delivering power to the end users. In conclusion, increased adoption of DERs is inevitable, and it causes issues in the local grids. The traditional wire solutions are risky investments, so we can look at traditional non-wire solutions like demand response. However, existing demand response programs may overlook the local issues of the grid because they are looking at the wider geographical area. So we are proposing a local demand control system which shows potentials to prepare local grids for more DER adoption. So these are the research on progress. Some parts are already done, particularly the types of loads that are crucial for the LDC system and a must. It pertains to its contribution to the LDC system. Advanced algorithms are currently ongoing, while the future topics could be scaling up the wider grid. For example, if you want to optimize your grid distribution operation by setting up the particular power demand level at different transformers, you can do that. And then you can also apply vehicle to grid in the future. And we can also test the system on an actual local grid with more houses. Another topic could be cost benefit analysis versus alternative solutions and market structure for shared value for all stakeholders and policy requirements. Currently, our team is actively talking with potential partners in the industry to develop this system and bring it to reality. And that's all I'm going to present this afternoon. Thank you for your attention.
Thank you very much, Ryan. That was an incredibly interesting presentation that really challenged our thoughts on load control, how we go about it, and turning it all on its head. So that's really quite innovative. So I've got time just for a couple of questions. Perhaps I can start off. Just a question on your control system there. From what I could see, the transformer was providing the information on the demand, but you're using the devices in the house to respond to that. So it's almost like I could say a dumb signal, but all the smarts are in the devices that are receiving it and making the local control decisions. Have you ever thought of what it would be like the other way around if the transformer was making the decisions and controlling the plants in the house? Was that an option that you considered?
Yeah, we actually thought about that, but somehow it would require all of the information from the houses to be sent to the transformer area. And it's one of our design criteria that we will not collect data from the end users. So we let the control dongles instead do the decision making by just giving feedback on the actual status of the transformer or the grid at the transformer area.
Okay, very good. Thank you for that. It reminded me of a report I read 2 or 3 years back of a study done in England called Electric Avenue, where they had a whole series of Nissan Leafs, and they made a controller, much as you spoke about there, but to control the houses locally, and got very similar results to yourself, something like a 40% plus saving in peak demand. So that could be hugely beneficial. No more questions coming in. Well, I'll ask you another quick one to finish then. The mechanism you used to send the signal to the house was was it just a basic tone over the LV? Had you considered other systems such as IoT or radio-based communications between the transformer and the devices in the installation?
Yeah, so we look into different communication options. One is what we considered and settled on is the power line carrier. And this will actually inject signal through the neutral of the transformer, and it will go through all of the 3 phases. We use this because we thought that it's faster, and it makes more sense because it already makes use of the hierarchical structure of the local grid. So we only inject the signal here, and it will naturally go to all of the devices on the houses. So we don't need to know which house belongs to which transformer. And I think we also considered doing it through the internet, but yeah, the issue is that sometimes the Ethernet can go down, and another issue is that it can be prone to hacking. Yeah, so we end up doing the power line carrier, which uses the inductive power transfer, which are the expertise, I think, of my colleagues.
Okay. Well, thank you very, very much, Ryan. That's all we have time for. A really exciting approach you've taken there. We will watch as an industry with great interest to see how this takes off. And thank you once again for taking the time to present your research work to us.
Thank you for the opportunity.
Well, as we move on to our next presentation now, this will be given by Gareth Williams, who is the Chief Product Officer for Solar City. Now, the title of this presentation is The Role of Third-Party Owned Distributed Energy Resources in Building an Efficient Grid. So this is a case study. Now, Gareth is the Chief Product Officer, as I said, at Solar City, and he leads the development of the Solar Zero platform, which provides services to homeowners, business owners, and the electricity industry as a whole. He's got more than 25 years of experience in the energy sector, with the last 15 years focusing on new energy technologies. Now, Gareth has had multiple leadership roles, or senior leadership roles in the electricity industry, and the information technology and network management, strategy areas. And he also has a degree in engineering and a postgraduate qualifications in renewable energy system design and energy management. So Gareth, over to you.
Yeah, thanks, Roger. Yes, so thanks for the invite to speak at this conference today. It's a great opportunity for us to share what we've been doing with this audience in particular, which I hope you'll find interesting. So we'll just get straight into it. So let me just get this sharing. Okay, so as Roger described, that's the title of this presentation. So what I'm going to do today is to really talk through really what our business is, what we've been doing, what the impact of what we've been doing is on the electricity grid, and talk about where some of the future potential lies. So just very briefly in terms of our company, we've actually now rebranded to Solar Zero rather than Solar City. That happened between the time I submitted my summary of what we do and today. So we're now called Solar Zero officially. The company started, in fact, many years ago, about 35 years ago, initially in solar hot water with Arthur Williamson from Canterbury University. This technology was being used. We've moved into the solar PV space probably about 6 or 7 years ago with an objective really to try and help the country move to 100% renewable. The whole basis of the company philosophically is to remove the cost barrier for customers adopting these distributed energy solutions such as solar and battery storage, and to provide customers with choice in terms of where they get their electricity from. So when the company was formed, our early investors were Stephen Tyndall, who was still an investor. We've also got ACC as an investor, together with Pencaro Capital, who invests on behalf of a number of investment funds. So that's sort of who we are. In terms of the size of who we are, we've currently got 4,500 plus customers. Most of those now have a battery. So we started off as a solar only company, but we switched to adding batteries in with our solar system for all new customers about 2 years ago. And we've gone on retrospectively where customers have wanted us to add a battery into their service. So we've only got 400 solar only customers left now. We're adding around sort of 200 customers a month currently. And that's roughly what we've got. So right at the moment, we have in the order, getting close to 25 megawatt hours of battery storage distributed across the country. The basis of our service is we install the panels, the battery system, an energy monitoring and control platform, which controls the battery, but it also does control the hot water cylinder. We're about to add in EV charging. Probably we're looking to add in heat pump control, etc., into the same platform. So the concept is we own and manage all of the hardware for the life of the energy services agreement, which is currently a 20-year agreement with the customer. We also provide the grid energy component, so anything that the solar and batteries aren't providing. The grid energy is also provided through retail partners that we work with. And we've got an e-store where customers can access energy efficiency appliances, again, through partners. The value that we add, our typical year one bill savings with customers adopt our services somewhere between 10 and 30%. To be fair, at the moment, more towards the 10 end, but we're about to change our pricing model, partly driven by the decreasing cost of equipment, where we're moving to an average saving on a customer's energy bill of 20%. The service obviously provides backup power to customers during outages to critical circuits in the home. The energy cost itself doesn't go up for 20 years. So the only inflation on the electricity, on the customer's electricity cost for the whole 20-year term is lines charge changes. And we guarantee savings across the whole 20-year term. So that's our service. I mean, a key question is really how do we save customers money? And there's sort of, I guess, three main areas. One, obviously, we're producing energy from solar, which is avoiding the cost of grid electricity and lines charges when the solar is actually being used in the home or stored in the battery for later use. And solar energy now is in a typical home is probably generating, energy in the 13, 14 cents a kilowatt hour range now. So it is cheaper than, the combined cost of grid and of energy and lines charges. So that's the first way we save. We're obviously using the battery to charge when energy is cheap and discharge when energy is expensive. So you know, it's not unusual to see a graph on the top left where the energy price, you know, is low in the morning, it comes up during the day and then decreases in the evening. So we're taking advantages of those, of that energy arbitrage. And also on networks, and most do now, offer time of use pricing. So we make use of those to, again, trying to minimize the amount of grid energy that customers use during the peak pricing periods. So overall, that's sort of delivering, you know, a saving to customers. Now, right at the moment, our product is based on a monthly fee that customers pay us, and then a low-cost grid electricity bill for the rest. We're going to be moving to a different pricing structure in the first quarter next year, where customers will simply pay a cents per kilowatt hour rate for all their electricity that they use, regardless of where it comes from, whether it be from the roof or the grid. We believe that delivers a much more simple proposition to customers. It makes it very easy to compare, you know, our solution with other retail grid options in the market. And as I said, we're moving towards an average 20% saving on our rate. So for example, we've just been doing the analysis over the last couple of days on some of the key markets. In Auckland, when you blend in daily charges, etc., customers currently pay around sort of 24 cents a kilowatt hour for electricity on average, and we're moving to about 19.5 in Auckland for all energy that customers use. So that's how we save customers money. In terms of our platform, as I described, we put solar panels on the roof. The average number of panels we put on to a system on a house at the moment is 12, so about 3.5 kilowatts of generation. Our current battery is in the middle there. It's a 6.4 kilowatt hour battery with a hybrid inverter, all the isolators, etc., all within a single cabinet. So we've designed our solution to be very quick to install, very neat from a customer point of view. There's no sort of additional components, you know, all being wired through conduits in a visible way. So everything's all installed within a cabinet. We have our monitoring system for ourselves and our customers, and we collect a ton of data. So we're collecting data in 5-minute increments, and that data we're collecting is including load, you know, solar generation, battery flows in and out, hot water loads in the home, voltages, both of the battery and the grid. So we have a huge data store in AWS that we're able to use for analytical purposes, which we do regularly. So what does our system do? So this is just a random customer, which explains in graphical way what our systems are doing. So if we start off on the left of the summer graph, and winter's the same, there's just less sun essentially. So we typically would be charging the battery from the grid in the early hours of the morning, typically between 1 and 5 a.m. Then it's 7 a.m., which is when we see grid energy prices and time of use lines charges starting to have an impact on price. So at that point, we are discharging the battery and working together with solar to try and offset as much of the grid import as we can. And as you can see in the early morning, the red dots are showing the average grid import for this customer over the summer months, and there's not very much. So we're able to get rid of most of the early morning peak. During the day, the solar is generating, offsetting loads in the home, and then exporting. You know, when the battery has filled up. So the order of priority is that the solar will support the home load first. If there's excess, it will charge the battery, and when the battery's full, it will export. So you start seeing the battery filling up late afternoon, and therefore export starts increasing. Every day we do top up the battery from the grid, typically between 3 and 5 o'clock, to make sure that the batteries are 100% full ahead of the evening peak. So in summer, we don't have to do a lot of grid charging. You can see there is some green, which means on some days there was insufficient solar to get the battery 100% charged by the peak by 5 o'clock. So we top it up from the grid. Then in the evening, we do what we do in the morning, really. We still, in some cases, using a bit of solar in the evening peak to offset load. The battery does the rest. The grid import is typically only when the home load exceeds the capacity of the inverter, which is currently 3.6 kilowatts. So if the home load's above that, we are forced to draw in some from the grid. And then the battery just keeps discharging to offset load for the rest of the day. And then we start again the next day. The winter's exactly the same. We just, as I said, we have less solar generation. In terms of the numbers, in the solar, in the summer, the battery enables us to use close to 70% of the solar generated, and the rest is exported. In a typical solar installation without a battery, it's like those numbers are likely to be the other way around. Where 70% is likely to be exported in the summer. And there's only less than 10% of the grid energy that is needed in the home in the summer was during a peak period, as defined by the network peak pricing periods. In the winter, we get to use nearly all of the solar, either directly or stored in the battery. And even in the winter, only 20% of the home's energy import has come from, during peak periods, has come from the grid. And that is predominantly a limitation of the battery capacity, which I'll talk about later. We're moving to fix that problem, if it's a problem. So just getting into some more detail, on terms of, what's going on. This is just a random customer in Christchurch, 9,000 kilowatt hours per annum. They've got 9 panels on their roof, 1 battery, and this is in October. So that purple line is showing their unmanaged load, effectively, in the home. So some peaks, obviously, it looks like hot water cylinder coming on and off. I don't know, it looks like it's coming on quite a lot during the early hours of the morning. Maybe a leak, don't know, something's happening. Not much during the day, block of load in the morning, and then an evening peak. So that's the first view. The next view, I'm overlaying a few things. So the load is still there. The orangey browny line is showing what the battery is doing. So if you follow that along, it's charging early in the morning. It's discharging, to offset load from 7 a.m. It's charging from the solar, during the daytime. It's doing a little bit of discharge during the day just to sort of offset some of those peaks. Then heavy discharge during the evening. The green line on the top is showing the battery state of charge. So the battery has reached sort of about a 30% state of charge in the early morning. We charge it up from the grid to 100%. It discharges back down to about 40% after the morning peak. Then it charges up during the day, reaches fully charged, in this case, by right on 3 p.m, which is useful. And then it discharges all the way down to sort of 10% through the evening and into the night. So what that does to the grid profile is it really pretty well gets rid of most of the peak. So we've now actually got a morning peak between 1 a.m. and 5 a.m. for this customer. But from about, as you can see, from 7 a.m. onwards, there is next to no grid energy required in the home. There's a little bit in the evening again, between, there's a peak there around 6 p.m, a little bit of grid import. And again, that is purely limited by the capacity of the inverter to offset the home load. And in this case, the battery, reached, its minimum state of charge around 8:30. So at 8:30, it was starting to import from the grid again. So again, in this case, it probably needed to be a slightly larger battery, but you can see the impact that it has on the customers, on the grid energy profile. The other thing, as I said, we do provide is backup power. So we typically wire in 2 or 3 key circuits in the home, typically all the lighting circuits in the circuit with the refrigerator or the televisions, etc. We wire into a critical load panel, and we're able to supply power during an outage. the phone app that customers have, indicates to them during an outage, if they keep using energy at the current rate, how long the battery will last, and gives them tips on what they want to do if they don't think 32 hours of backup power at the current rate is going to be sufficient. It's one of the forgotten benefits, I think, of our service until there is an outage, and then we get a lot of very happy customers emailing in, which is a nice thing to happen. So I think, it was interesting listening to Murray's presentation earlier, talking about the work that EEA did and looking at the different value streams from batteries. And we've, following the same path, really. The interesting thing from our point of view is that we can make the economics of solar and batteries stack up just on the customer value side of things currently. So we're not really needing additional revenue for our business model to work. However, being a commercial organisation, we like the idea of additional revenue. So that is something we are pursuing. But from a purely financial point of view, we're not relying on some of these grid service revenue opportunities from the solar and batteries. It's already working. It's already working for customers. But I think there are some key opportunities in terms of how we can use some of ours and other organisations managed and owned resources to help with some of these grid services. So just talking on some of these. So on the key one we have been working with Transpower on is demand response. And as Murray alluded to earlier, batteries are sort of interesting because they actually have a multiple, they have a dual purpose. They are at the same time load and generators in the same box, if you like. So there's potentially, demand response available from discharging more power from the battery. There is demand response potential from charging from the grid less. And then when you add those two together, that gives essentially what the available demand response potential is of a battery throughout the day. So we've got a lot of available demand response, in the early morning and later in the afternoon, because we can stop charging the battery and start discharging from the battery. So in the morning and evenings, we've got up to 4.5 kilowatts of available stored capacity to provide demand response. But even in the morning peak and the evening peak, there is still, even in the middle of winter, there's still up to 1 kilowatt on a fleet basis, on average 1 kilowatt of available demand response capacity per battery. And that's without any pre-notification. So if we knew that there was an outage coming, it was a planned outage, or there was known to be a network issue that was going to cause an issue later in the day, and we have an opportunity to charge the battery or not discharge it, then we can provide, significantly more than that. But this is just purely based on an unpre-planned demand response capability. Our platform we built has already got demand response capability, so we can override any of the schedules for a group of batteries, and that can be done on anything from an individual site to a whole network, to a GXP, or to a whole region, or any other sort of aggregation that we create within our system. So we can select a whole group of batteries. Our system then allows us to set what do you want to do? Do you want to charge, or do you want to discharge? On what date and time do you want that instruction to last for, and how fast do you want the battery to do whatever you're telling it to do? So if we know that it's likely to be a 4 or 5 hour event, then we would reduce the power setting to say to just 1 kilowatt, knowing that we're going to have adequate battery capacity to be able to act right through that event. So this is an event that we ran with Transpower, a real one in Hamilton, and you can see the bars up until the event shows typically what the batteries were doing, and then on the event, we can see we were able to increase what the battery was doing based on its normal operation. And this was during a normal evening peak period without any pre-notification. So it sort of was showing how much we could respond just by overriding what the batteries were normally told to do. So some of the key opportunities that, as we see them, so what this slide sort of combines two bits of information. One is our new battery that we've prototyped, and we're looking to move away from a fixed 6.4 kilowatt hour battery solution into a more modular solution where there can be up to 4 or 5 kilowatt hour modules. So we'll be able to design the storage to suit the customer's energy profile much more accurately, to make sure that there's enough storage to get through all of the or most of the peak periods without running out. The other thing we're also doing is on the inverter side, we're going to have a 3.5 and a 5 kilowatt inverter, again to allow us to sort of match the solution to the customer need. I mean, that's really what's enabled us to do this, is just an ongoing decrease in the cost of batteries. So effectively, being out at, we're almost at a point now, where we've made another step change in the cost of, we can put in a 10 kilowatt hours of storage for not much more than the 6.4 kilowatt hours than we currently do. So I think this modular batteries approach, I think, suits our model well, and is supported by some of the modeling from the data we've got. So in terms of, where we see some of the key opportunities to work with networks, and we are working with a couple of networks currently, is to look to, so at the moment, I mean, our approach is scattergun. We just put we sell nationally, we put batteries and solar systems in where there's demand from customers. But if there are areas of networks where there is an upcoming network investment, potentially, working with us to try and get a significant uptake of solar and batteries solutions into a local area, provides a very cost-effective way of managing increasing peak demand at relatively low cost, because, financially, the systems have already funded themselves. So, the contribution really from a network is to provide some financial support to help us drive, bigger penetration rates in that local area. So we would be using those funds for, for very targeted marketing campaigns, potentially to sort of implement an additional sales incentive, with our solution to try and get the volume that we would need. So that's, a really exciting opportunity that, as I said, a couple of networks we're in discussions with in terms of applying that solution.
Just 4 minutes to run, Gareth.
Yeah, it's going to work out well. The national and local demand response services, as I said, we're already working with Transpower. We're about to add in all of our battery fleet into the demand response program. And with those same lines companies, we're also working to look at how we can use the batteries for local demand response services. The key issue is just technically how does the network communicate with us when there's a demand response event? So we've just started work on that in terms of how do we integrate, SCADA systems into our platform, which, is doable. It's something we haven't built yet, but will. The next on our roadmap is, and we've already had some discussions, with Transpower / system operator in terms of using batteries in the reserves market. And yes, at the moment, they can really only participate as interruptible load, but there's definitely, potential for them to be providing, energy back and, exporting energy as well as stopping charging. The key thing we were looking at is the fast response, so local measurement of frequency at the home and sort of very instantaneous response of the inverter batteries to that frequency measurement. So that's some work that is scheduled to start second quarter next year. And then there are other network services that Murray as already described, really around frequency keeping, voltage support, etc., that we're also interested in looking at. I think there's another interesting opportunity, I think, working with the electricity industry more broadly, is just the amount of data that we have, which, we do have 5-minute load data at individual homes. We have solar data, we have hot water, heating information. So we have visibility of when people's hot water heaters are on. We have voltage measurements, both of the battery, which is largely irrelevant to the industry, but certainly we have network voltage measurements, which again could be interesting. So, so overall we are very interested in working, with the industry. I think the resource, is has significant value if it's deployed carefully. Our business decision to move to batteries was in no small part in recognition of the fact that solar without batteries is actually relatively detrimental to the grid, and so we did make an early move into batteries, recognizing that solar by itself we didn't think was really a sustainable energy solution for New Zealand. So that's partly why we batted batteries in. So that's me, I think, pretty well where we needed to be.
Thank you very much, Gareth. Incredibly interesting. We can see that solar is here and it's here to stay, and as an industry, we need to work with you guys to get the maximum benefit out of this. I haven't seen any questions come through yet, and we're almost out of time, but I just had a quick one for you, just a real high level question. I think it was back at Murray's talk, he was just talking about the rates of EV and PV penetration in New Zealand, and perhaps a surprising thing for me, and just recall I'm coming from the West Coast, we're not known for our high sunshine hours here, but the thing for me was just seems to be a linear increase in the PV penetration in New Zealand rather than an exponential or hyperbolic. Yeah. Why is that, and what do you see the future for solar as in New Zealand?
Yeah, it is interesting. I mean, we're not following the same adoption curves, as you would see in other parts of the world where it is more exponential. It's a good question. I mean, if I'm being a little bit controversial, maybe, I think, in many cases, some of the incumbent generators haven't been useful to the case, and there's in our view, a lot of misinformation in the market and in the media in terms of the financial value of solar, and I think that's put some people off. I think the New Zealand message that we're already very highly renewable hasn't had the same therefore impact as it has had in other countries where solar is deemed to be a solution to climate change. We have maybe less of that environmental driver, possibly. I think some of it is, has been, is still the cost of solar. For a lot of people, it's out of touch. I mean, we in our case, we've seen fairly steady growth. We're hoping our change of pricing approach will allow our proposition to be much more obvious to customers in terms of it delivering savings than it might do. I think it's just one of those things where we just haven't reached the, that magic tipping point yet. And I think, when we're sort of looking towards, getting to a 20% savings number on customers' electricity costs, I think that's starting to we're hoping will become more interesting to customers. But yeah, I think those are probably the key reasons. But it's just purely the financial incentive hasn't been strong enough yet. But I think that's coming pretty quickly.
Thank you very, very much, Gareth. Sorry, we couldn't spend more time. Lots of interesting questions, I'm sure, would have been forthcoming, but we appreciate the time you took to present that material for us, and we're sure we'll hear a lot more from you and your company in the years to come.
Oh, thanks, Roger.
Okay, well, our next presentation today is entitled Utility Scale Battery Energy Storage System Grid Connection. Now, this is going to be presented to us by Harshal Patel, who's an associate in power engineering with Becker. Now, Harshal is a chartered professional engineer. He's an experienced a project and design manager, delivering large multidisciplinary projects across industrial, transport, transmission and distribution and generation sectors, a man with many skills. His current focus is on the advisory and delivery of renewable energy projects across Australia and New Zealand. This includes renewable energy microgrids, low emission energy hubs, and grid connections for large-scale solar battery energy storage systems, solar farms and wind farms. So, Harshel, over to you.
Thank you for the introduction. I'll just share my screen. Just let me know when you can see that. Oh, where's my screen gone? Sorry, give me a second. Can you guys see my presentation?
We're seeing your presentation screen rather than just the presentation itself, Harshel, if that makes sense.
Yes. So let me know if that's better.
That's better.
Ah, right. Perfect. Yeah. So yeah, look, I lead the grid connections team at Becca as one of our market leaders in energy and renewables. I thought it'd be a good opportunity today to share with you some of the key considerations and challenges with grid connection of a large battery storage system project we're currently delivering in Australia. I guess with the New Zealand Ministry of Business, Innovation and Employment, I guess having approved funding to investigate possible energy storage solutions to New Zealand's dry year electricity problem, I felt that it'd be great to come and just share some of these key considerations and challenges that I've personally faced, and I guess from a grid connection compliance perspective and what that could mean for New Zealand. So the three key areas I want to, I guess, run through today are really around system strength, technical performance standards, and battery storage operation as a generator and a load. So firstly, the first consideration is around system strength. So what exactly is system strength? Some define system strength as a measure of the network's ability to maintain voltage levels during fault conditions. And it's a combination of system inertia and system short circuit ratio governed by the availability of generation to system fault level. And it's important because it enables network to maintain voltages during network disturbances and faults and keeps generation connected. I've always struggled to really understand what system strength is, and I've found a nice rock and jelly analogy to explain exactly what system strength is to help I guess bring down to layman terms. So consider a rock. If you prod a rock, nothing happens. Anyone else touching the rock would be unaware that it has been prodded. This represents a very strong system where if a network disturbance occurs, there's very little voltage fluctuation. Any generators connected to the grid will not see much of a disturbance. Conversely, a weak system behaves like a jelly that wobbles when prodded. The wobbling is felt throughout the jelly and not just at the point of contact. Voltage is highly sensitive to any network disturbance, and depending on how many generators respond to the initial disturbance, that could end up creating additional disturbances, which kind of leads to a snowball effect where voltage distortion increases to such a state that generators start to trip, creating further disturbances and leading to what is a worst case scenario, which is a system blackout. And I guess as we transition from large synchronous machine-based generation to inverter-based technology, system strength is becoming an increasingly important consideration. So how do we improve system strength? One option is to install a synchronous condenser. And I think Murray mentioned, a synchronous, it's a spinny thing that's connected to the grid. So it's essentially a synchronous condenser is a synchronous generator that doesn't produce any real power, and it's specifically designed to actually provide reactive power for system strength support in response to network disturbances. And this is a common solution amongst developers. However, it does come at a high upfront capital cost, which can actually tank the project before the grid connection, during the grid connection assessment process. And a common hard pill to swallow is that, you know, the benefits you provide to other parties connecting in the same region. So, you know, you fork out the cost for your project to install a synchronous condenser to improve system strength, to allow you to your generating system to connect to network, but then you actually provide that benefit to other parties wanting to connect as well. However, they don't have to pay for the cost of the synchronous condenser. So it is quite a hard pill to swallow, and it does come up to, you know, consideration around stacking, you know, stacking your economies and looking at your return on investment. Other options include synchronous storage, such as pumped hydro, which could be used to not only provide, you know, stored energy, you know, to provide energy storage, but actually system strength remediation. And obviously, developing a pumped hydro system comes with obvious challenges around costs and environmental factors, but, you know, the benefits could outweigh the challenges under the right context. Other options are special protection schemes to actually curtail the generation output or trip under certain network conditions, such as condensing events. This doesn't directly improve the system strength, but tripping of inverters under the right conditions will prevent the system strength from worsening. Again, it is a trade-off against the cost of development against revenue from generation. However, there's an opportunity to, you know, I guess, increase your total nameplate export capacity as network upgrades and augmentations occur over time, allowing to export more without curtailing or running the risk of being tripped off. Another one which is becoming more common is grid forming inverters, which aim to replicate the function of synchronous machines through synthetic inertia. So in Australia, there has been a couple of cases, particularly in South Australia, where they have trialed grid forming based inverter systems using synthetic inertia to prop up system strength. And it's very common amongst island network arrangements. But yeah, as system strength, it's becoming more common as well, just as a system strength remediation solution as more inverter-based generation is introduced onto the network. The next is around technical performance. So technical performance of the generating system is another important consideration when assessing the grid connection requirements. You know, power quality and ride-through capability are some of the more important performance standards that need to be well demonstrated as part of the grid connection assessment, which I'll touch on these you know, quite briefly, just give you a bit of context. So around, I guess, quality of electricity generated, you know, harmonic voltage distortion is becoming increasingly common due to the inverter system, which is considered to be a source of harmonics, as because they are switching, you know, power electronic devices. In Australia, the transmission network service providers actually provide the emission limits at the point of connection. So it is quite transparent for developers, you know, regarding performance that you need to demonstrate as part of the grid connection compliance process. From a flicker perspective, this is not much of an issue for battery storage, just due to the constant energy source that is available, you know, which is actually stored in the batteries itself. In New Zealand, the Electricity Participation Industry Code does not actually state the harmonic emission and flicker limits at the point of connection. And I guess this is both an opportunity and a risk, as it makes it easier to navigate through the compliance requirements. However, the effects of power quality, you know, due to harmonics are observed locally. And if, you know, I guess people start to complain about power quality issues, then it'll be up to, you know, yourself as the, you know, the asset owner to rectify it to an acceptable limit. Which, you know, can lead to additional costs, which may not have been able to be factored, which could have been factored otherwise. So, you know, a lot of people are looking at, you know, allowing for, you know, harmonic filter banks as part of their project. Whether they need it or not is a different, I guess, is a different issue. But I guess a lesson learned, particularly with one of the projects that we're developing in New Zealand, is allowing for it in the event that over time, if I guess voltage distortion becomes an issue, there's a provision for installing a filter bank to offset or rectify the issue. The next one is the ability of a generating system to ride through and remain connected during network disturbances. So in Australia, particularly, I guess in the network electricity market on the East Coast states, it is a requirement to demonstrate continuous uninterrupted operation for frequency, voltage, and contingency events on the network. And look, out of those three, demonstrating response to contingency events can be quite, is actually quite challenging. It is dependent on a number of contingency scenarios the network service providers prescribes, and includes planned and unplanned outages. And that also includes looking at other committed generation as well in the network and considering that as part of the contingency events. And to automatically qualify for this particular performance standard, there's a requirement for generating systems to remain connected for up to 15 disturbances within a 5-minute window, and that includes a combination of frequency and voltage events. So it is quite it's quite a high bar that's been set in terms of being able to remain connected during contingency events. In New Zealand, the EPIC clearly defines the ride-through capability requirements in the North and South Island as no trip zones, as per the following graphs. And this is taken directly from the code. There's also a separate diagram which also demonstrates how long you are required to remain connected when you consider a trip at Haywards and Benmore for an HVDC contingency event as well. So quite useful and quite clear as well as part of planning for large renewable energy integration. And lastly, I wanted to quickly run through charging and discharging scenarios for a battery system, which is also, can be also applicable to pumped hydro or any other form of storage. And that is considering a battery storage system as a generator or load. And I think Murray touched on this briefly as well, this in the previous presentation. So in Australia, the battery storage systems are actually required to demonstrate technical performance both as a generator and as a load, which makes sense, right? As a grid connector system, when you're charging, regardless from the grid or if you're co-located with a solar farm or wind farm, it acts as a load, and when discharging, acts as a generator. So when acting as a load, some of the performance standards that need to be considered are, power factor, balancing of load currents, voltage fluctuations, harmonics, and load shedding facilities, typical for a large HV connected customer. So nothing unusual there. But I guess from recent experience, it has been quite interesting to negotiate performance standards for power factor and load shedding, given the battery is operating both as a generator and as a load. So as a load, the battery system at its nominal voltage is typically required to operate within a power factor range of 0.95 lagging to unity. However, for a specific operating scenario when the battery is charging whilst also providing voltage control capability, the power factor may very well operate outside of the permissible range when it's attempting to control voltage, which is contradictory in terms of the, I guess, prescribed performance standards at this time. From a load shedding perspective, if the demand is in excess of 10 megawatts, there's a requirement to provide automatic interruptible load shedding in response to falling system frequency. And however, if the battery is contracted to provide FCAS services or frequency keeping services, then you want the system to be able to remain connected to provide a measurable response to support frequency instead of being disconnected. So again, another area where there's a bit of contradictory in terms of being a interruptible load from a load shedding perspective, whilst at the same time the ability to actually provide frequency keeping services to keep the system propped up. And look, from that experience, I believe there's further work to be done through industry participation with the regulators on defining suitable performance standards for hybrid systems, such as battery storage, pumped hydro, and other future, I guess, energy storage systems, particularly as more and more non-network solutions are incentivized. So I guess in summary, system strength shortfall, it's becoming an increasingly common problem as Australia transitions to a more decarbonized future. And again, particularly with New Zealand, as we start to invest more in wind and solar, it will become an issue. And this is just an increase in, I guess, due to the increase in distributed renewable energy resources with inverter-based technology, and it's coupled with the retirement of coal and gas-fired large synchronous-based generation, which would otherwise prop up the system network with system inertia. And what this is causing is a headache with developers having to fork out additional cost due to implementing system strength remediation schemes, which include costly synchronous condensers. There is a notion in Australia for network service providers to invest in improving system strength so they can actually incentivize new connections and remove the burden of any one party forking out a cost of remediation schemes for the benefit of others. I think in New Zealand, it's probably less of a problem at this stage, just due to the large number of interconnected synchronous machines we have, particularly with our hydro schemes across the North and South Island. But something that we still need to consider in terms of system strength at the point of connection when looking at a more utility scale sort of project. Demonstrating continuous uninterruptible operation in response to contingency events is also challenging, just because the network service providers dictate the number of contingency scenarios, and as I mentioned, it's becoming increasingly more complex due to a number of other committed generators that you need to factor in when doing your system studies. New Zealand, no trip zones have clearly been defined in the EPIC for North and South Island, but again, still need to consider the contingency events and scenarios and the ability for your generating system to remain connected for specific disturbances. In a system that can operate as a generator and as a load, such as batteries, it is stuck like a rock in a hard place with contradictory requirements and performance standards, and further work is required with industry stakeholders to actually define what is an acceptable means of demonstrating performance under certain operating scenarios. And I think, given that we're about to invest more time and research into what the New Zealand big battery would look like, whether it's a large battery system or pumped hydro, I think there's an opportunity in New Zealand to get ahead of the curve during the early phase of this investigation to define what acceptable performance standards could be, as this leads, this can lead to complications during the execution phase and include, impacts to transmission pricing methodology. So look, there's an opportunity there to, work with Transpower and others around defining what acceptable performance standards, are required or can be, particularly as we move towards, large battery, pumped hydro, or anything else that could start to help support the dry years that, that we're currently facing. And that's all from me. Any questions?
Thank you very, very much, Harshel. And what's more, you've brought us right back on time too with your nice succinct presentation. Incredibly interesting. You've obviously faced some real challenges. So we've got a few minutes now for questions for Harshel. So perhaps I could start off from a technical perspective, because obviously you're very technically into all this. Harshel, you mentioned originally the maybe a synchronous condenser, which has rotating mass.
Mm-hmm.
And then you talked about grid forming inverters with the ability to provide synthetic inertia. Is that with or without a battery, or how do they work?
Yeah, so with synthetic inertia, there's a lot of, a number of inverter manufacturers out there that you don't actually require a battery to provide that inertia. I still think it's relatively new technology, and I don't understand fully the mechanics behind it. But my understanding, it's all software based to effectively counteract, compensate for removing fault level from the system.
Okay, so does it do that by adjusting the voltage rather than injecting any real power? Yeah,
that's right. Yeah. So it's all based on software to essentially measure, what's there on the grid, and then compensate by negatively injecting or positively injecting to balance that out.
Very good. We have a question that's come in. From your experience, what would you consider a low SCR that could affect control of the inverter?
Yeah, so in Australia, I think an SCR of less than 3 is considered to be very low. And that's where, that's where the threshold is set in terms of you have to provide a system strength remediation scheme with an SCR of less than 3. Anything higher than that, if you can demonstrate through system studies that you will not have an adverse impact or do no harm to a system, you've got more justification there to not provide any remediation schemes. But yeah, I think SCR of 3 is definitely the industry's threshold. So the specific project I was talking about here with the battery that we're currently working through a good connection, it's currently connected in a region with a system strength of 12, so very strong. So we're able to, I guess, easily negotiate, not having to provide any sort of system strength remediation schemes, even with other parts of network, I guess, harming the network from a system strength perspective. Given that the region that we're in is so strong, we're able to, I guess, easily negotiate that out.
Cool. No, thank you for that. I had another question for you around one of the points that you raised there, Harshal. You talked about let's say the competing requirements for connecting a battery in terms of the connection standards. You talked about when the battery was operating as a load, there was a power factor constraint, but when it's providing support, there wasn't. What do you see as a potential solution to that? For instance, what's wrong with just letting the battery work under voltage control rather than worrying too much about power factor?
So I think it's just the way the rules are currently prescribed at the moment. The rules have been, is definitely tailored around generating systems. But when you I guess when you introduce something like a battery system, which can operate both as a generator and as a load, or as a hybrid system, the rules aren't very clear on the applicability of those rules to such a generating system. So I think what needs to happen is just more clarity around defining a generating system as a solar battery, coal fire, gas, and whatever it is. I think just needs to be better clarity around these are the specific standards that apply. If you have a generating system that considers a battery, the following standards apply and the following standards don't apply. So it's just the rules I think are very good already as they are. It just further clarity needs to be defined specifically for batteries, I think.
Okay.
So what we've found is, we've been able to demonstrate the performance requirements required for battery operating as a generator. And when we came to trying to define, or I guess demonstrate the performance in line with the rules for a battery acting as a load, or what they call customer performance standards, we found for those specific ones I spoke about around load shedding and power factor, that they were, we couldn't actually quite 100% meet them as per the rules, just given the nature of the system. So AEMO, the Australian Energy Market Operator, recognised that those rules are slightly, I guess, contradictory in terms of how it's written at this point in time. So there's definitely industry stakeholder participation currently going on at the moment to actually define or help define better to make the connection of battery storage projects easy in the future.
Okay, thank you. Now we have time for one more question, and because no one's raised it, Harshal, I get the privilege of asking you the last one as well.
No worries.
It surprised me when you said that the code in New Zealand, the EIPC, currently doesn't state limits around, I think, harmonic levels at the point of connection. So you almost left to work it out yourself to some extent. Do you see a possibility there of something like, let's say, the EEA power quality guide, which does provide those sorts of limits, that we could use something like that as a de facto standard? Or do you think we really need to work hard to get the code amended to include those limits?
Yeah, look, I think there's a bit of ambiguity in the code itself, and it's largely just due to the fact that historically New Zealand has been primarily I guess a hydro-based generating system sort of country. As we kind of move more towards inverter-based technology, we've got a number of wind farms in development at the moment, and in New Zealand, coupled with a couple of large solar farms, and as we move more into future with distributed energy resources, the inverter-based technology, introduction to the grid will start to mean that there's more and more, I guess, considerations that need to be made around harmonics. So again, look, it does come down to, I think, industry participation and stakeholder consultation around whether we look at merging the limits prescribed by the EEA and whether that needs to be included into the code or vice versa. But look, currently, and this is particularly an example that was drawn from a project where a wind farm we're developing in New Zealand, and working with the wind turbine manufacturer on compliance. There's one of the things that we came across as I wouldn't say a challenge, but something that wasn't very clear in the code to begin with. So again, it is a risk and opportunity, but definitely I think there's opportunity there to help define what those limits could be to help further connecting parties in the future, kind of meet compliance, and I guess help from an investment perspective as well.
Well, thank you very, very much, Harshel. Once again, on behalf of the whole group, I'd like to express our appreciation for giving such a clear demonstration. We'll never forget you from now on, your rock and your jelly when we talk about system strength. So we appreciate that. Thank you.
No, thank you for the opportunity.
Well, we're just about right back on time now. So by the time I finish the introduction, we'll be ready for Glenn. So Glenn Sullivan is the Group Manager, Electrical Engineering for Fonterra. He's going to be talking to us today about the electrification of dairy processing, insights, innovation, and impact. Well, just a bit of background on Glenn. He's the Group Manager, Electrical Engineering for Fonterra. He leads the asset management function across the whole Fonterra group. And he's got a particular interest in large-scale electricity use in the dairy industry as a means of achieving a low-carbon future for Fonterra and related industries. Glenn's a registered engineering associate. He's a member of Engineering New Zealand, and he has a bachelor degree in economics. So Glenn, over to you.
Yeah, hi everyone. Firstly, thank you for the opportunity to share my presentation with you today. This presentation is not particularly technical at all. It's more about sharing our story and our journey to date around decarbonisation and electricity's role in that and what we see happening in the future. So that's my job today, is to share that journey with you. Okay. So firstly, just a brief introduction to Fonterra. We are a dairy company. We're about taking New Zealand based dairy products and taking them to the world. A few metrics just to paint a bit of a picture about Fonterra's operation in New Zealand. This is a New Zealand centric view. We collect almost 20 billion litres of milk from around about 11,000 dairy farms, shareholder owned dairy farmers around New Zealand. Using a privately owned tanker fleet of about 530 odd tankers. Our peak day, so I don't know if everyone's aware, but the dairy industry is very seasonal. We have a peak just like the electricity supply industry. We build things to peak. So we have a peak, it happens in spring. So protein rich spring grass growth is the best time to produce milk. And on a peak day, we collect around about 80 million litres of milk. We process that milk into quite a wide range of different products, but they broadly fall into three groups. Ingredients, you can think of that as milk powder really. Food service, which is like restaurants and takeaways is a good example to use. And consumer branded goods, so stuff that we buy individually inside the supermarkets. Manufacturing wise, which is what I'm here to talk about, we use just a shade over 20 PJs of energy in total per annum. And I guess one of the other key takeaways from this slide is that we do have a pretty significant focus on reducing greenhouse gas emissions, as well as some other environmental metrics. So that's sort of Fonterra and who we are and what we do. In terms of greenhouse gas emissions and our decarbonisation journey, Fonterra specifically, and I guess the dairy industry generally, and I should have made a comment at the start that I often think that Fonterra is a reasonable proxy for thinking about the dairy industry in New Zealand generally. I'm not there to speak obviously on their behalf, but I think it's a reasonable view to hold. We are a fairly significant contributor to New Zealand's overall greenhouse gas emissions profile. So, Fonterra's dairy operation contributes close to 16 million tonnes in carbon dioxide equivalent per annum, which represents about 20% of New Zealand's entire gross greenhouse gas emissions. So it's really significant. Most of that greenhouse gas emissions occurs on farm. So at the bottom of the slide there, you can see sort of a breakdown of where these things occur. So on farm is very significant. This is methane and nitrous oxide from the livestock. What I'm here to talk about is the 10% in the middle, which is still very significant. and there's also 1% related to distribution. So a little bit more detail. The same information really, but just presented with a little bit more detail. You sort of look at that centre bar through the middle of the slide. There's an attempt to illustrate what the total greenhouse gas emissions are across New Zealand. And again, you can see that the green bar at the top there around our farmers' agricultural emissions are a fairly significant part of New Zealand's overall contribution. And the two call outs at the bottom there, Fonterra's transport emissions, not as significant as what I first thought they would be, to be honest. When I think about the size of our tanker fleet in particular and the amount of product that we actually distribute and ship around New Zealand. But the manufacturing emissions, so this is on our manufacturing sites, again is reasonably significant, and so along with an awful lot of work that's going into the on-farm emissions, there is a huge amount of effort going into our manufacturing emissions as well. So again, just a bit further detail. I'm not too sure how well those North Island and South Island graphics show up. I hope they show up. They're a little bit pale on my screen. But this is an illustration of where we currently use or how we currently source our energy for our manufacturing operations around New Zealand. So we have sort of manufacturing plants, sites dotted from Kauri, which is just north of Whangarei, all the way down to Edendale, which is about 40 kilometres north of Invercargill. And the size of the dots on the maps there, they represent the relative scale of the energy use on those sites, and the colours also indicate what the energy source is. So the South Island is always a really good place to look. So Edendale in the south is the largest consolidated dairy site in the world, and its thermal energy use is entirely supplied by coal, as are all of the other South Island sites. So no reticulated gas system in the South Island, and to be able to raise an awful lot of heat, coal is sort of the only economically viable. Well, I shouldn't say that any longer, but for a long time, coal was the only economically viable option for raising an awful lot of heat. In the North Island, of course, we have gas. So the green dots there represent sites that have gas supplies to them. There are 3 sites in the North Island that are showing as burning coal at the moment. So this slide is just slightly out of date as of August 2020. One of those dots is now wood biomass, which is a huge step forward for Fonterra. So Te Awamutu, site at Te Awamutu, we still do burn some gas on site, but at least gas has half the emissions footprint as coal. And what we were using with coal has been fully replaced by wood pellets. So it's been a great step forward. In terms of scale, we have around about 550 megawatts of coal boiler capacity in the South Island, and probably about another 100 megawatts in the North Island. So I think one way to sort of grasp the size of the issue that Fonterra is facing with the greenhouse gas emissions from coal in particular is that if we took all those coal boilers and we dismantled them and decommissioned them and replaced them with electro boilers. Electro boilers are considerably more efficient. We would still be looking at something in the order of somewhere in the high 500s, maybe 585, 590 megawatts of electricity to replace that coal use. Now, I'm not suggesting for a moment that that's what Fonterra is going to do, because it's not, but it does help illustrate the significance of the issue that we're grappling with. And just a little bit on process heat use at Fonterra. This is where the vast majority of our energy uses go, and it's certainly where the greenhouse gas emissions originate from. An awful lot of our plants dry milk, so we're pretty much just taking the water out of milk. So you take milk and you evaporate the water off it, and when you've got sort of 20 billion litres of the stuff, it takes an awful lot of energy to do that. So that's where this massive need for thermal energy comes from. In terms of electricity use at Fonterra, as an aside, lots of pumps and fans, very mature technologies. We don't do anything too smart or clever with electricity. And our electricity use is around about 17% of our overall energy use. So there's no question that heat and heat raising absolutely dominates our energy use at Fonterra. So not surprisingly, we have some targets that we're seeking to achieve in in reducing our greenhouse gas emissions, and they are largely aligned with the Paris Accord, which of course New Zealand has signed up to. So firstly, something we're quite proud of is we've had an energy reduction program for some time now. We wanted to reduce our energy use by 20% by 2020, which we've materially achieved. 2020 being our Fonterra financial year, which finished in July. So I expect there'll be more in the public domain about that before long. But very, very pleasing that we've, like I say, we've achieved that. But certainly looking forward, we have a 30% reduction in greenhouse gas emissions by 2030. And we've also brought forward a pretty significant commitment that that Fonterra has made. So we originally did have a 2030 target of not installing any further coal burning capacity or coal boilers inside Fonterra by 2030. Last year, Fonterra made a commitment to make that commitment effective immediately. So as of last year, we will not be installing any further coal boilers, and we want to achieve a net zero emissions by 2050. And the energy trilemma, I guess, applies equally to Fonterra as it does to everybody else. We need our energy supply to be secure. Milk is a perishable product; we can't stockpile it. So when we're especially in the peak of production, a secure energy supply is very important to us. We do want it to be sustainable, and that's the pathway that we're on. At the same time, it does need to be economic. We are often a commodity. We face commodity markets, so we're a price taker. If we price ourselves out of that market, we do believe that we risk carbon leakage out of New Zealand, and that all that will happen is that milk production will go to some other jurisdiction, perhaps where there is not the same focus on sustainable outcomes as we're trying to achieve in New Zealand. So, like everyone, we just want our energy cheap, we want it secure, and we want it green. If we get those three things, we would be very happy. So our journey to date in trying to achieve that, and electricity's role, and that, like I say, on the left there, we have had an energy reduction program for some time. It's been very effective, so we're banking that, but we're continuing the focus. In 2017, we put together a roadmap with the Ministry for the Environment, along with some other key stakeholders, including Transpower. And out of that, we determined that there were two broad approaches that we were going to pursue in addition to the energy efficiency. One of them is around greater use of biomass. And I mentioned earlier that we're now doing that at Te Awamutu, and we're also co-firing a little bit of biomass at the top of the south at our small plant at Brightwater. So they're great achievements. And in terms of electricity use, we went to Edendale, which is the large site down in Southland. We went down there with the University of Waikato and some input from the University of Massey from a dairy process perspective. And also Transparent. We spent a few days there trying to understand what would it actually look like, if we completely remove coal off site and replaced it 100% with electricity. How would we do that, and what does it look like, especially from an economic perspective? And the outcome from that was some quite surprising findings, and also the commitment that we would trial that at a pilot site. So in 2018, Stirling, which is a much more modest size site, but also in Southland, or Otago, we determined that we would make Stirling coal-free. And we thought at that time that electricity would be the right fuel to use in place of coal. So we went to Stirling to work out how we could completely remove coal off site, and we replace it 100% with electricity. Now, we had some quite surprising learnings out of this. First of all, I guess just to illustrate how we thought this was going to work. And the way to read this graph is that the thermal energy use along the bottom there, made up of various colours, at the moment at Stirling, runs at around about 11 megawatts. So I think we've got there 10.73, which is surprisingly accurate for a presentation, but let's call it 11 megawatts. So we have 11 megawatts of coal currently being used on site at Stirling. Our electricity use at the moment is represented just by the blue bar at the top, so that's about 3.4 megawatts. And the various initiatives that we identified are illustrated across the bottom. So I won't bore everyone to tears with what the first two are in terms of changes to dairy processing, but it's effectively what those two initiatives are. So the first one was to convert from thermal vapor recompression to motor vapor recompression, which is basically doing away with some steam and replacing it with some electrically driven fans. And the way to read this graph is you can see an increase in the electricity at the top, so that light green color. It looks like it's gone up about 800 kilowatts or thereabouts. And you can see a corresponding reduction in the thermal bar. So the same light green color in the thermal bar is the reduction. So for a relatively modest increase in electricity, oh, sorry, it's only half a megawatt electricity, 450 kilowatts. For a relatively modest increase in electricity use, there's a pretty significant reduction in the amount of steam use on site. So that's a pretty big one. And then likewise, as we make our way across the slide from left to right, our water heat recovery, effectively no increase in electricity demand at all, but a decrease in steam demand of around about half a megawatt or a shade over half a megawatt. Things get a bit more interesting, I think, around the heat pump technology, which is more ubiquitous and applicable to far more industries than just the dairy industry. We sort of see them in sort of two spaces, sort of 55 degrees and 85 degree heat. And we're seeing coefficients of performance now approaching sort of more than 3, which is really exciting. So we thought the thing to do was to use a bit more electricity. Again, you can see that increase on the yellow bar there, and a really significant reduction in steam use. And ultimately, what we are left over with, though, is that there is still some residual steam demand for various processes that require a higher grade heat than what can be achieved with industrial heat pumps. And we thought the thing to do there was to use a smaller package electro boiler, which had some fantastic technical attributes, but are hellishly expensive to operate. So that's what we thought when we went to Stirling. That was our original plan. Unfortunately, things have changed. What we actually found when we got into detailed design engineering is that each of those 3 main options they brought with them some particular challenges which we didn't foresee until we got into sort of detailed design. Heat pumps, for example, what we found was that procuring heat pumps and installing them and commissioning would follow sort of a project path that we originally envisaged, and there was no great issue with doing any of that. But what we found was that the heat source for heat pumps does not always necessarily line up with the time that you need a heat sink. And so the first thing we had to do was to put in some kind of heat storage. So, a large tank somewhere with hot water in it, for example. The other thing that we discovered is that heat sources and heat sinks around a dairy plant are actually spread out a bit further than what we first imagined. And that while we understand stainless steel very well, we found that pumping hot chlorinated water around the site actually requires some kind of high carbon steel, certainly outside my area of technical discipline. But what I do understand is that high carbon steel is a whole lot heavier than stainless. So what that meant was very significant structural upgrades on pipe bridges and the like to carry all this additional weight. So unfortunately for us, what we found with heat pumps is that while we understood what it would take to procure and install heat pumps, all of the balance of plant meant that the total project cost came in at roughly 3-fold what Fonterra first thought a heat pump strategy would cost on a site where we're trying to retrofit this type of technology. So heat pumps suddenly became really quite unattractive in terms of retrofitting. Unfortunately, we found similar issues with converting from TVR to MVR. What we found was that the thermal vapor recompression unit is quite a small thing, and the motor vapor recompression is actually quite a big thing, so we couldn't physically fit it inside the building. And what that meant was, in effect, a 2-story building that has to be big enough to carry the weight of quite a heavy piece of equipment, and also be clad and accessible for maintenance and operation and the like. So again, what we found was that the total capital cost of installing a TVR to MVR conversion was sort of in the order of 2 times larger than what we first imagined it would be. Electro boilers, nothing really further to add electro boilers other than that we know that they can be very expensive to run. So for Stirling, what we learned was that actually heat pumps are not as economic as we thought when it comes time to retrofit them on an existing plant. And likewise, some of the other dairy process changes that we've identified can be considerably more expensive to retrofit as well. So what that meant was a much larger electro boiler, which in turn, of course, also quickly became quite uneconomic. Sort of 11 megawatts of electricity, where the operating cost of electricity is roughly 3 times higher than that of coal, makes for a pretty poor business case as well. So I guess just to finish off the story around Stirling, Fonterra has changed direction. So we're looking in some detail now at a biomass boiler in place of coal. So we are committed to Stirling being coal-free, and we will achieve that. It is very likely that now the technology that Fonterra will use to do that will be a biomass boiler. So the key message for my presentation today, and we're trying to share this with the electricity supply industry, is that Fonterra is not quite so bullish as what we were perhaps 2 or 3 years ago on increasing electricity use as part of our decarbonisation journey, particularly in the South Island. And in fact, we actually see biomass taking more of a front seat really in our energy future, particularly between now and 2030. I guess so. That's the key message for us. We sort of observe others noting that they see the far greater electricity use as part of the decarbonisation journey, and we agree for lots of applications, but certainly not process heat and dairying to the extent that we thought it would. From here, what we imagine is that where it does make sense to retrofit things like not retrofit, but to install things like heat pumps or to retrofit TVRs with MVRs, we will take those opportunities where they're economic. And certainly any new plants that get built, these are the sorts of technologies that would be designed and implemented on day one, rather than trying to fit them into an existing plant later, which we've discovered is really, really difficult to do. So I think that's pretty much my presentation. Thank you very much, and thanks again for the opportunity to share the message. Really happy to take any questions that anyone might have.
Thank you very much for that, Glenn. It's great to have a perspective from maybe outside the electricity supply industry from one of our key users to understand what your drivers are, what you need to achieve, and hopefully that'll give us a few ideas on how we can work together to support you in your decarbonisation strategy. So it's time for some questions. Now, I had one just to start off, just to get the ball rolling. Just looking at coal, so you're trying to move, say, from coal to biomass, I just got from your presentation. Coal has an energy density of, let's say, 24 megajoules per kilogram. I'm not sure what biomass is, probably somewhere around 2. So has anyone done any sort of calculations on the amount of biomass that would be needed around the country, or how you deal with that? Or would we even produce enough to fire all of the, let's say, biomass-fired boilers for Fonterra in New Zealand?
Yeah, it's a great question. It's a question that comes up frequently. But please bear in mind I'm the electricity guy for Fonterra, so okay. I'll answer the question the best I can. But I guess there's a couple of things and that I heard in your question. One of them is, the energy density, and you are of course right. Wood biomass is, depending on how wet it is anywhere from sort of 30% to 60% of coal, except where it's been pre-processed. So the wood pellets, for example, at Te Awamutu are approaching actually the same energy density as coal. So in terms of being able to get it to our sites, the number of vehicle movements and the like is not really a lot different from coal. But certainly if it's forest residue, it's quite a different story. We do have more vehicle movements to get that much energy to our sites. In terms of availability, the short answer is yes. There is enough residual wood biomass available that is economic in the South Island in particular, and also in the North Island for the few sites that have coal still on them. So except for there's a bit of a gap, sort of in the early 2030s for about 6 or 7 years. Now, that's not to say that the energy is not available. It's just that we go up the value chain in terms of the wood biomass that we would burn. In effect, as we understand, the wood market, if I can call it that, at the moment we would basically be buying saleable logs and we would be chipping them and burning them. between now and then, you know, we believe that we can get enough other wood residue to not have to, you know, take high value, you know, logs and burn them for fuel. But the short answer to your question is yes, there is enough.
Okay. Hopefully no one else wants us access to the same same heat source, but that's cool. Thank you for that answer. I just had another question for you now around heat pumps, maybe more on the process side. My understanding of milk powder drying is most of your, let's say, your high pressure steam, the high temperature steam is used for the actual final dryer. What opportunities would you see for the use of heat pumps, even if partially being used to heat the dry air?
Yeah, it's something that's been looked at for quite a long time, I understand. Certainly, the exhaust heat is a great heat, you know, source for heat pumps to even use heat elsewhere. I probably can't comment further on the viability of preheating drier air using heat pumps. We're more likely to use the exhaust as a heat source rather than, you know, as a heat pump technology for preheating dry air at the moment. Right, okay. I think there's greater opportunities for heat pump technology than dry air preheating.
Yep. Look, I understand that. I've read an interesting study lately done at a technical university in Denmark, trying to look at options for milk powder drying. And with MVRs, there's a lot of good heat you can recover off of those for preheating air. As you said, the dryer exhaust is a great source of heat for heat recovery. But they also then put on a heat pump to boost it up, and then the final stage is always a problem, just to get to that 220 or 210 degrees to dry your milk. Yep. So I've always wondered why we use steam to do that heating. It just seems inefficient to me, even with an electrode boiler, to heat steam to heat air to dry the milk. Any comments on that?
Yeah, we have a number of direct electric air heaters now, cool. And they're quite large.
Yep.
They're a little bit problematic. I guess scale becomes a really big issue. So in New Zealand, we have the largest individual dairy plants in the world by a factor of 2. So at Edendale, Darfield, and Litchfield, the 30-ton an hour dryers. So you know, Fonterra and others are definitely pushing the scale when it comes to dairy processing. In terms of creating a direct air heater, electric element air heater, if you like, on that scale, it would it's never been done. So we're definitely in the R&D space, and I don't think that Fonterra has the appetite, and probably nor should we, to be in the space of doing research and development in air heater technology for direct electricity use. When electro boilers, for example, are quite a mature technology, there's an industry out there that does a really good job of producing really great electro boilers, and the efficiency of that supply chain, if you like, is actually pretty good. So we already have the existing infrastructure for all of the large air heaters and those large dryers. Yep. If we were to use electricity as a fuel switch, the thing to do would just be to put a large electro boiler in place at about 98% efficiency, and continue to raise steam and not face all of the capital cost of a large electric air heater and all the risk associated with it.
You know, we understand. Thanks, Glenn. Yeah. We have one final question. It's in from Sean. With the proposed strategy after learnings from Stirling, what is the expected increase or decrease in electrical consumption across Fonterra or at a site level?
Well, yeah, it's a great question too. So the short answer is we're doing that work right at the moment. So I think the Stirling experience has forced us to go back and have a bit of a rethink around some of our bigger sites. So quite literally last week was Clandyboy, another big site. And Edendale was about a month previous. So we are revisiting some of the original plans. So we call them green prints. You know, what is the green print future for these sites? and the jury is still out a little bit on what electricity uses role is on those sites. But it is a bit more modest than what we first imagined, and I think where we sort of arrived without committing to pursuing this path just yet, but it makes for a great example is that we can take about 30% of the coal off site at Glandyboy with about 7 megawatts increase in electricity use using heat pump technology and the like. So I certainly have the sense that it's around about that scale. So Glandyboy, for example, at the moment it's a 30 megawatt site. So by 2030 we might be using around about 37 megawatts, for example. But we do need to beat the path again of making sure that 7 megawatts can actually be installed economically, and that's the work we're now doing.
Well, thank you so much, Glenn, for coming along and speaking to us about this interesting topic. And we're going to look forward to working with you as an industry in the future in your electrification pathway.
Thanks for the opportunity.
You're most welcome. Looking forward now to a special presentation from Nigel Wilmot from Western Power. Now, Nigel is the Senior Standards and Technology Engineer for Western Power, and he's going to be talking to us about voltage management and inverter settings, the West Australian experience and approach. Now, Nigel's been working as an engineer almost as long as me for over 28 years. He started off at Murdoch University, and his research was focused on standalone and grid connector inverter energy systems. And then he worked on developing national and international standards for these systems. Over the past 12 years, he's been working for Western Power and influencing the Western Power approach to the management and connection of small-scale energy systems into the grid. It's been through his work with the AS/NZS 4777 standards development that, this has been through his work with that standard, the Western Power connection requirements, as well as responsibility for power quality and voltage strategy work. Now, this year, Nigel was the recipient for the 2020 National Meritorious Contribution Award. I wish we had one of those in New Zealand. This is one from Standards Australia and has been awarded status as a Fellow of the Institute of Engineers Australia. Over to you, Nigel.
Thank you. Good morning, everyone. It's just after 7 a.m. in Perth here. I'll get stuck into my presentation. I'll just get the screen up and sharing. Hopefully that's come up on your screens.
Yeah, all good, Nigel.
That's good. Okay, so my bit of background for Western Power first. Western Power delivers energy to an area about the same size as New Zealand, according to Google, but to about 2 million people. Our peak load during the hottest part of summer is about 4 gigawatts. But traditionally we had a minimum nighttime load of about 1.3 gigawatts, but that's now changed with the increase in DR hosting we have on our network. We're looking now at a daytime load, which is a system load, what our central generators send out, of 1.1 gigawatts. On the slide there, you can see that we've got when the slide was produced, 1 gigawatts, but now it's more around getting close to 1.4 gigawatts. And we've got over 1,000 battery systems, individual battery systems installed across our network. So what does Western Power do? We're essentially the poles and wires business, connecting the central generators to our customer loads who are connected via retailers. With such a large spread out grid, we are changing what we're doing. we're changing from a centralized grid model into a dispersed model with using microgrids and standalone power systems. In the future, where the population is concentrated, we'll have the mesh grid with power delivered from the standard sources, which will continue. And then the light grey area in this picture will become a mixture of standalone power systems, microgrids, and what we call the autonomous network.
Excuse me,
so,
Nigel.
Yep.
I'm still just seeing your front page.
Oh, really? Sorry. Oh, sorry about that. I'll just, don't know what went wrong there. Okay.
Depends which one you share with Zoom, doesn't it? There we go.
Okay.
Much better. Thank you.
That's it. Yep. Okay. Sorry about that. So yeah, look, information there and the size of the grid where we're located and what we do. Just cover that. And this is probably more what I was just talking about. Thank you for picking that up. Look, so we've got, as you can see, the dark grey areas where we're going to continue to have our traditional networks, whereas the light grey areas potentially areas where we will still supply electricity, but using standalone power systems and a combination of microgrids and a lot shorter networks than we have at the moment. So managing this transition has, and particularly with increasing renewable energy and DR from customers, which is uncontrolled sources of energy, you can see that we've got some challenges. The key challenge for us at the moment is over voltage. And this, with the changes to the Australian standard for inverters and Australian New Zealand standard for inverters, when the upper limits of the voltage range are starting to be reached, to manage the voltage within the installation, the inverter output is constrained. And this is driven by the power quality and safe voltage levels within the installation. The second one, which I previously mentioned, is our daytime load is dropping down to 1.1 gigawatts, with our largest generator being 1.3 gigawatts of mostly solar. Some other things that has caused us to rethink the way we plan our network is network capacitance. We're getting to a point where our central generation is being called on to absorb more and more VARs being supplied from the load. And this change is a combination of a decreasing load level, increased voltages. Also, our load has changed from a lagging power factor of about 0.9 to 0.95, driven by motor loads and other inductive type loads, to everything, even your humble washing machine and refrigerators are now powered by a variable speed drive type device, which has power electronics, which runs at unity and at lightly loaded situations. So basically looks like a capacitor to the grid. So peak load no longer is poor power factor. We're recording peak loads, or at our peak loads on individual distribution transformers, we're usually seeing unity power factor at peak, which completely changes the characteristics of things. On top of that, we've got a voltage obligation that was set close to 100 years ago. And that voltage obligation is constantly maintained within plus or minus 6%. So a little graphic there does a little bit of comparison. what we have to deal with, a voltage range which is 254 volts to 226 volts. Then the compliant for Australia, who's got a sort of halfway transition to the international standard, has a +10 -6% range of 253 to 216 volts, and then the European range, they actually, in their power quality standards, allow +10 -15%. As you can see, our WA range is the top half of the international range. So essentially, a network which was designed for one direction flow is now being asked to go in two ways. And one of our strategies of managing it is transitioning to a different voltage standard. And that we're working with our government to do that. I believe New Zealand is sitting at 230 volts ±6%, which is, will have the same challenge as we have, which is a limited range. However, you don't have the issue of when you do go over voltage, the voltage in New Zealand is still a safe voltage. Whereas when we start to go over voltage in WA, we're starting to potentially significantly decrease the life of appliances, and it's a less safe voltage range, over voltage range. So having discussed this with many people, I came to realisation that in Western Power, there's a culture of considering voltages under 230 volts to be bad voltage. So we went out and did some research and some testing at the University of Wollongong, who's got a power quality centre. And we looked at a range of voltages and testing right down to 184 volts. And we found that all equipment actually still functioned correctly at that voltages, and there was no safety issue. So sitting, dropping to below 226 volts, which is our traditional level, we've got a comfort now to go that way. Also, for the last 20 years, equipment has been manufactured to the Australian voltage range. So there's, people with equipment greater than 20 years old potentially need to replace that. The larger range will enable us to manage our voltage at a much lower level. Now, if you're not familiar with PV and the way we design networks, typically we design substations, and this is with voltage sitting at just above 1 per unit on the MV level, and at the transformer LV terminals we sit at just under the upper limit to allow for voltage drop along our networks down to 240 volts or lower at peak times. As you're aware, things have changed. Now we have to repurpose our network for two-way power flow. And you can see in this example that when you connect PV and at 100% hosting capacity, it's not much reverse flow will then cause us to have a voltage which exceeds our limit of +6% or 240 volts. And so there's quite a large swing from one end to the other range, and that's very good. A network's good for it. It can handle the two-way power flow. It's just the way we have traditionally set our voltages up the higher end, and that is what all utilities and DNSPs around Australia and internationally do. As you can see, I did mention earlier about the two-way power flow. the middle of the day load is being eaten out in the centre of the day by the ever increasing solar curve. And unlike South Australia, who can depend on their neighbours to provide frequency, and neighbouring states provide frequency, a 100% renewable supply is a challenge that Western Australia will need to deal with, as we still need synchronous generators to provide an system inertia, provide system stability and keep our grid afloat. So we've got several aspects to our strategy and from DR, and the two things on the left there, you can see that network voltage rising as we get more and more distributed energy. Load is lighter on the end of the networks, and the source is flowing the reverse direction, which is forcing our network voltage up. And then the other issue with decreasing proportion of inertial generators on our network, we have concerns about system stability going forward. First, we're tackling the short-term stuff, which is the set and forget solutions. All about what are the settings we need for that high penetration future. We are also looking at storage solutions, and eventually we'll go to a distributed service distribution service operator, a DSO, and real-time control and interventions on managing load and generation. But today I'm just going to focus our short time, about 20 minutes, on set and forget solutions. And the two key ones there are voltage management and also inverter power quality response modes. So at the moment, the number one challenge for us is our tight range. So the WA Distributed Energy Resources Roadmap has foreseen that they will change the legislation to remove the voltage reference plus minus 6%. And the most likely outcome there is they'll go to the Australian standard, which is plus 10 minus 6%. Western Power and others will be, and EEA members will be looking at changing the Australian standard to the full international range in the coming years. The other thing that we're doing is we've dropped the voltage. No longer is our starting point on the LV network at 250 volts. We now adopt it between 5 and 10 volts. And so our starting voltage on networks is starting to be in the range of 240 to 245 volts. And this was being done by changing automatic voltage control points on a zone substation transformers, and also on our downstream distribution regulators. We also, because we then have a challenge of undervoltage, we'll continue to do power quality programs to address poor performing areas. And also, if you don't measure your voltage or you don't look at your voltage, you've got no idea how you're performing. So we are involved in an annual benchmarking project, which is focusing on power quality issues, looking at harmonics and flicker, and also with a focus on voltage. And that's showing us that over that trend that we've been trying to do is coming down with the voltage, and we're starting to get close to being compliant with our existing range requirements on the upper end, but increasingly getting non-compliant with our lower voltage range, which is an issue that we need to address, taking into account economic considerations and funding operation of our network. Also, that a voltage of 220 volts is a safe voltage, so that's difficult to justify increasing increasing the network or investing in the network to fix sort of safe voltage. We also have trials and management technology. We've got 13 on-load tap changing transformers at the LV level being trialled at the moment, dealing with the issue at the source, and also utilising 14 community power banks at the moment, and looking at deploying up to another 100 of those community power banks to address reverse power at the micro level. At these are about 100 kVA, 400 kilowatt hour community power banks. Since 2015, we have a 10 volt reduction across our grid. What we're going to do in the future, AMI, Advanced Metering Infrastructure, is a real tool that we'll be utilising greater, which will enable us to target where the real issues are and get us more measured points to understand the voltage compliance across our network. Reactive upgrade. What I mean here is when customers reports a potential fault or fault, we'll go and check for safety and non-compliance issues and target those areas for upgrades. And then another area which we're developing, and is a whole presentation on itself, is the way we're using risk-based and probabilistic planning methods. We're developing something called the GT-Eng, which will look at it's able to model our whole network. We're under various scenarios, which allows us to combine all our economic factors in with engineering factors to determine the most optimal arrangement for our entire network area, which allows us to predict where we need to change from that change into an autonomous network or retain mesh network. And that takes into account population, other drivers and economic drivers to determine where the load will be in 10, 20, 50 years' time. Also, the investigation of other enabling technologies, and one of the big areas is control of distributed energy resources, DR, into the future. The other thing is need to balance what the customer's expectation is as they continue to install about 5,000 new systems a month into Western Australia. And part of that is the development of appropriate inverter standards. And as you can see, hopefully, if all the standards Australian Standard New Zealand Board approves it this month, we should have AS477 2020 published before Christmas or shortly thereafter. In that standard, there's been some improvements with including new and refined withstand capabilities to enable improved grid stability. So undervoltage ride-through, frequency withstand, like some of the key areas that have been added. And also we've developed regional settings for PQ responses. So not one size fits all. Different issues are experienced across the nation in Australia, and also New Zealand has a different voltage range. So again, separate set of settings for New Zealand. And to make sure that these settings work, there's been a lot more detail on how the PQ responses and the withstand capabilities are tested when you certify inverter. The first WR regional setting we're using is a volt-watt response. This starts at 250 volts, which is 4% above our nominal voltage, and it cuts off and it slopes down to 20%. So after the voltage at the inverter terminal reaches 250 volts, the inverter will start to reduce its output to ensure that the voltage within the installation doesn't rise significantly above our upper limit. This is a slightly steeper slope than what we've had previously. As we are now, with the reduction of voltage on the network, we're hoping that the target is our 250 volts is what we can call our V99% level, whereas our V100% level is 254 volts. The next setting, which again will help us with our network, reducing the absorption of VARs at the large generators and offsetting some of the local impact of the voltage rise of local DER with inverters, and also reducing the VAR supply from the distribution grid to the transmission network. Typically, we've got a fairly low slope where we reach 40% at 255 volts. And our normal operating range between 235 and 245, between 0 and 10% VARs, which is 1 to 3% reduction in output power. This is going to be fairly insignificant for most customers, and it won't impact on their ability to self-consume the energy. Putting those two responses together and including the grid voltage, I'll just put a point on to show you. Hopefully you can see the pointer. This bottom black line is the VAR response, power level against the rated kVA on inverter, so not 30%. So if our voltage is sitting at the lower end of our range, then we need inverters to help boost the voltage by supplying VARs. And then during the normal operating range, we expect inverters to absorb some VARs. As you can see, the actual, depending on the grid voltage and the voltage drop, with a 25% self-consumption, you're looking at 246, which is up on the upper end of our operating desired range. Those potentially could start reducing. Most customers have a lower voltage drop in their network, in their installation, than 2%, which we've modelled this on. And so 1% of the time, customers can expect some reduction in the output. But some other customers may find nothing will be affected. So our typical voltage range at the moment is this, but going forward, when we get a legislation change, we're going to be sitting between 230 and 240 as our target. A range which allows us to have quite a bit of voltage rise on our network during a peak DR, but also with an extended range, hopefully we'll still be able to drop the voltage also. Just rounding up everything, voltage range management. Those limits, it's not necessarily the nominal value, but the limits that impacts the flexibility of the grid to host DER. We've got an onus on us to meet compliance, and we've got a strategy to ensure that we do, but there's onus on customers to operate systems to offset impact of the generation on the grid also. I like the development of harmonic standards is a great example of that. the underlying philosophy of our harmonic standards is customers install equipment that meet the compliance harmonic standards, and networks provide networks which can handle those equipment. If there was no harmonic standards and networks was supposed to provide a clean waveform, that'd be impossible because the load would be distorting it and it'd become uneconomic for supply of electricity. But by having customers spend a little bit extra on equipment, and insignificant because it's just become part of the whole industry and makeup of how we do things now, means that networks don't have to invest as heavily in networks that would need to supply clean harmonics, but there's still effort needed there. Similarly, taking up some of the impacts from PV and DR within the inverter and capability does not add a significant cost, and networks still investing in network, and it's a balance between those two things. And finally, the Western Power has coordinated the voltage strategy with DR settings balance cost to all customers versus cost to individual customers. Thank you for your time.
Well, thank you very much, Nigel, for getting up so early this morning to join us from Perth to give us that excellent presentation. Looks like you're facing some real challenges there.
Yes.
We've got time for just a couple of questions from anyone. I'm sure there must be some burning ones out there, but perhaps I could just start off with maybe a controversial one, Nigel, from a technical perspective.
Yep.
Around 4777. I noticed you said there that you've got the two control modes that cut in. One is around the watt control and one is around the VAR control, but you have the, as I understand it, you have the watts backing off first, and then as a secondary control measure, you do the VAR control, which is,
no,
is that correct?
No,
No, it's not.
No, the VAR control cuts in first.
Yep.
And the watt comes in later. So for the watt response, the VARs will be provided and starts at 235 volts, and that will provide that reduction in voltage. And then the volt watts commences at 250 volts, which is the upper end of our range, which rarely hit.
Well, thank you for clarifying that. That was quite controversial over here when we were looking at those regulations, and that's where we ended up as a country saying, let's go with the volt VAR control first, because it doesn't impact so much on the customer, and then focus on the volt watt control. So that's excellent. So
the volt watt control is a fairly sudden situations to make sure that the voltage within the custom installation isn't pushing the voltage up. Essentially, volt watt acts on the resistor part, and your most resistor part of your network is the customer installation compared to the network. And so it has more to do with the local installation rather than the whole network, whereas the VARs tends to contribute. VARs happening on one inverter won't do much, but what we're looking at is the VARs across the whole network being reduced and consumed by the thousands of inverters that we're getting installed each month, which is offsetting the need for us to install inductors and reactors on our transmission network.
Very good. Thank you for clarifying that. Perhaps just one final question. I understand that in South Australia at present, the middle of the duck curve is just sort of approaching very, very low levels. Do you see Western Australia ever getting to the same position?
Yes. We've got 1 million customer connections. We've already got about 300,000 of them with roughly a 5 kilowatt PV system on there. And if you innovate, eventually we'll have 1 million connections with a 5 kilowatt PV system on it. That's about 5 gigawatts, and currently we've got a 1.1 gigawatt daytime load. So the maths says we've got a problem coming up, and hence it'll be balance of other technology will be trialled, and hence we'll see many batteries installed across Western Australia on the grid, because we need grid in front of the generator, in front of the meter batteries, because we can control and deliver the services, the fault current and other specifications we need to safely run our network. One of the problems with behind the meter batteries and inverter equipment, they provide no fault current to the network. And that's going to continue to be a challenge until we come up with a solution or change our standards in the way we manage fault protection within customer homes.
Thank you for that. We just have one final question on the chat that's come in. Have you modelled voltage impacts upstream, i.e. extra VAR contribution required at zone subs due to downstream volt VAR mode?
Look, I think I touched on it briefly. No, we have looked at, we have been doing measurements, and traditionally 20 years ago, we had with air conditioners, the air conditioner revolution about 20 years ago in Western Australia, where our peaks were uncontrollably increasing because everyone could afford reverse cycle air conditioners, and they were very direct and line type compressor motors, and our peak load was very inductive, 0.95, 0.9 power factors, with the VARs being sourced from our generation. The modelling shows ever increasingly with the transition from overhead networks, change in customer load types, that we do have increasing VAR load of VAR supply from our low voltage networks. So yes, we have done modelling. We have looked at the impact of volt VAR, and it does make sense. It's cheaper for all customers to supply and absorb VARs locally than it is for Western Power to try and deal with the changing load and increasing decrease of the daytime load by installing traditional network elements, and anything we spend on our network eventually ends up the customer paying for it anyway due to the regulations.
Thank you for answering that question, Nigel. And thank you so much once again for joining us. Your wonderful work on AS/NZS 4777 that we're all going to benefit from when it finally gets through the process.
Well, hopefully it'll be my Christmas present this year, hopefully.
That's good. I'd like to thank all of our presenters now, and let's just have a brief sum up of the excellent set of presentations we've been able to enjoy this morning. Probably the best asset management forum I can remember in terms of content. It's just a pity we couldn't do it face to face. We started off with Alan Miller looking at utility scale PV, and wasn't that interesting to see the penetration? We could see gigawatts potentially of utility scale solar in New Zealand, and showing us where that could actually happen. Murray Henderson then talked to us about distributed energy resources, and he confirmed the short version was, yes, it does stack up in New Zealand. He referenced the Superi report, which I'll certainly be having a look at, and you might remember the value streams that we can have or create from distributed energy resources. We then moved on to Ryan Tuberling from University of Auckland, and what a great system they use to control load locally on our distribution subs, using smarts in the installation to monitor and control the load there, a distributed load management system. What a great thing for the new emerging technologies that are coming upon us. We then heard from Gareth Williams looking at solar penetration. It's a happening thing, isn't it? They're seeing 10% savings now. A 20% saving, that can be hard for a customer to look away from. We can expect to see increasing penetration of solar in New Zealand. But what interested me is how they can aggregate that and offer that to DSOs in the future. Harshal Patel talked to us about the challenges he's faced at Beca with integrating large-scale battery energy storage systems into the grid. The issues with the code, particularly around the lack of harmonic regulations, that more clarification was required, whether you're generating or you're a load. Glenn from Fonterra talked about coal and biomass. Maybe we're not going to see as much electrification with electrode boilers as we thought. Maybe we'll see some with heat pumps, but watch this space. And then finally, we'll just listen to Nigel, who talked about some of the challenges from the big country. 5,000 PVs per month, and our network would be lucky to see 5, so it's certainly a lot bigger. And yeah, we'd like to thank Nigel once again for his contribution to the standards, particularly around AS 4777. So once again, I'd just like to thank everyone for joining us today. Thank you to all our presenters. We hope that what you've heard today will help you in your strategic asset planning. Well, that brings our presentations to a conclusion now, and it leaves me just to wish you all a very pleasant afternoon. Thank you.